This n denotes the dimension of the invariant subspaces. But how we can find the dimension of the invariant subspaces? That is an important one. So then first we need to study what is the invariant subspace. So yeah, finite dimensional linear space, that is n-dimensional linear space Wn, is said to be invariant with respect to the differential operator f. This is a given differential operator. If f of Wn subset of Wn, that is f of u belongs to Wn for all u belongs to Wn. Given differential operator f admits an invariant subspace Wn, then there exist n functions psi1, psi2, psi n such that the f of linear combination of n linearly independent function we can write in this form, where the psi I are the expansion coefficients of f of u in Wn on the basis fi. In addition, we can assume that the invariant subspace Wn is defined as the space of the solution of linear nth order homogeneous ODE. So here, this is a Wn is a solution space of the nth order linear homogeneous ODE. If Wn is a invariant under the given differential operator f, then the invariant condition for the subspace Wn with respect to f takes this form. Because why? Because we are taking u in Wn, but Wn is a linear space. That linear space is a solution space of the nth order linear homogeneous ODE. So this L of u equal to 0 when f of u in Wn, because f of u also need to satisfy the linear homogeneous nth order differential equation. Therefore, we obtain this invariant condition 4. This where n is a natural number and the constants, the unknown constant an and an minus 1, etc., an, a naught are to be determined. But what is the dimension of the invariant subspace? That is important here. So we need to find the dimension of the invariant subspace. So the dimension of the invariant subspace is depends on the order of the given differential operator. If a linear subspace Wn is invariant under a nonlinear ordinary differential operator f of u, this is a given nonlinear operator of order k, then the possible maximal dimension of the invariant subspace is 2 into order of the differential operator plus 1. So n less than or equal to 2k plus 1. K is the order of the differential operator. So here one important thing is I would like to point out that the invariant subspace method allows one to reduce nonlinear PDE into system of ODE. The obtained system of ODE may be solved by the well-known analytical method. So here I am WNBI n-dimensional linear space over R. If the linear space Wn is invariant under the given differential operator f of u, then the given nonlinear PDE admits the following exact solution in this form, that is in finite separable form, where this aj of t satisfies the following system of ordinary differential equations. This obtained system of ordinary differential equation may be solved by the well-known analytical method. So here let us consider the well-known family of generalized nonlinear convection reaction diffusion equation. So that is in the form, the first term denotes the diffusion, the second term denotes the convection, the third term denotes the reaction. So the convection reaction diffusion term can be classified into three processes. One is convection, reaction, and diffusion. But how we can construct complete classification of invariant subspaces for convection reaction diffusion equation? Also, how we can derive exact solution using the obtained invariant subspaces. That is important here. So first I am considering generalized convection reaction diffusion equation. That equation 7 can be rewritten in this form. So the order of the differential operator G is 2. First, we need to define the linear space. Linear space is a n-dimensional linear space. That n-dimensional linear space is a nth order linear homogeneous ODE. But here the dimension is very important because dimension is depends on the order of the differential operator. But the order of the differential operator is 2. So already we studied the maximal dimension theorem in the previous slides. So the maximal dimension theorem gives the possible maximal dimension is 5 because n is less than or equal to 5. So the possible invariant subspace dimensions are 2, 3, 4, 5. So here we can discuss only the above values of n. So first we consider the invariant subspace dimension n equal to 2. So first I'm considering the two-dimensional invariant subspaces. Particularly I'm considering two-dimensional trigonometric space. So this W2 is invariant under the cubic differential operator. That means G bar of u is a cubic means where A of u, B of u, C of u satisfied this condition. So that this is a cubic differential operator. So this linear space is invariant under this cubic differential operator because it satisfies the invariant condition because G bar of u again in W2 because W2 we are taking that u is a linear combination of this. So G bar of u is again in W2. So therefore we can say this W2 is a invariant under the cubic differential operator. So, but how we can find this invariant subspace? That is very important here. So first I am considering the dimension of the invariant subspace n equal to 2. The differential operator G bar of G bar, given differential operator G bar from W2 to W2, where this W2 is nothing but a solution space of the second order linear homogeneous ODE, where this A1 and A0 are constant that to be determined. So for this case, the invariant condition reads in this form because it need to satisfy G bar of u is also the second order linear ODE and L of u equal to 0. Then only we can say this W2 is a invariant under G. So where G bar is given differential operator, this is a given differential operator. So if you are substituting the G bar of u into the equation 10, then the equation 10 reduces to this equation. But this equation gives system of overdetermined equation. Solving the overdetermined equation, we can get the complete classification of two-dimensional invariant subspaces with corresponding differential operator. So this is a procedure for two-dimensional case. Similarly, we can do 3, 4, 5, etc. The above system of overdetermined equation gives one set of solution, that is A1 equal to 0. So if you are giving here A1 equal to 0, this is a trigonometry subspace. And the A of u, B of u, C of u are in this form. So therefore, we can compute the two-dimensional trigonometry subspace from the linear ordinary differential equation. That is, W2 is a trigonometric subspace. So this is invariant under the cubic differential operator. So then we can look for the exact solution in this form, that is a linear combination form. You see C1 of t cos root A naught x plus C2 of t sin root A naught x. C1 of t and C2 of t are the unknown functions that to be computed. So here, the obtained invariant subspaces we can classify into polynomial, exponential, and trigonometry subspaces. First, I am considering the two-dimensional polynomial subspace. So when A1, A0 equal to 0, then we obtain the polynomial space, but this polynomial space is invariant under the cubic differential operator and the quadratic differential operator, because this first one gives the quadratic differential operator because G bar of u involves A of u, B of u, C of u. So therefore, the first one gives the quadratic differential operator. One gives the cubic differential operator. That means this polynomial linear space, polynomial two-dimensional linear space is invariant under the quadratic and the cubic differential operator. So similarly, we can construct expansal subspace. Here we can get two type of expansal subspaces. The first one type, that expansal subspace, two-dimensional expansal subspace, enter the three different quadratic differential operator and two different cubic differential operator. So this same invariant linear space is invariant under the three different quadratic operator and two different cubic operator. So the type 2 expansal subspace, that is a two-dimensional expansal subspace, is invariant under the quadratic differential operator. So note that if A0 and A1 that are arbitrary constant, then we obtain linear subspace that is invariant under only the linear differential operator, because if A of u is a B naught and B of u is C naught and C of u is a K1u, so this therefore we obtain only the linear differential operator. So next one, similarly we can construct the three-dimensional invariant subspaces. So we can assume the dimension of the invariant subspace n equal to 3. So first we can calculate the polynomial subspace. So the three-dimensional polynomial subspace is invariant under the given differential operator, that is a quadratic differential operator. So the three-dimensional polynomial space is invariant under the quadratic differential operator. So exponential, three-dimensional exponential subspace is invariant under the quadratic differential operator. Similarly, we can construct the three-dimensional trigonometric space that is invariant under the two different quadratic differential operator. But here we can consider n-dimensional linear space. The n-dimensional linear space is a solution space of the nth order linear homogeneous ODE. But here I need to point out that if dimension of the invariance of space greater than or equal to 4, then we obtained only the following linear differential operator. So this operator, that means this Wn is invariant under only linear differential operator. So so easily we can write, because this nth order ordinary differential equation, we obtained n linearly independent functions. So phi 1x, phi 2x, phi nx are the linear independent solution of m linear ordinary differential equation of order n greater than or equal to 4. For the convection reaction diffusion case, we are obtaining dimension of the invariant subspace is greater than 4, then we are getting only linear differential operator. So if dimension of the invariant subspace less than or equal to 3, we obtain both linear and nonlinear differential operator, given differential operator g bar of u, along with parametric restriction. The possible nonlinear differential operator with their corresponding invariant subspaces are discussed previously. The linear differential operator that is given in the previous slide. So this linear differential operator 12 is invariant under the that means the differential operator is given that admits the following invariant subspaces. This following invariant subspaces n less than or equal to 3 also. So here I need to point out that, so the given operator is a linear, then we don't need to think about the dimension of the invariant subspaces, because here dimension is not a problem for linear operator. So the linear operator, this is a convection diffusion equation operator, that linear operator admits the following invariant subspaces that we can classify polynomial, exponential, polynomial and exponential, and trigonometry subspaces. The last one is a more general one. This combination of polynomial, exponential, and trigonometry subspaces. So here the n is a natural number. Here n is not the dimension is not a problem for linear operator. Suppose in case I'm taking k not equal to 0 for this operator. So this operator admits the following invariant subspaces. That is also here we can classify polynomial, exponential, polynomial combination of polynomial and exponential, trigonometry. So we can write all the combination. So the last one is a more general linear space that is involving exponential, polynomial, and trigonometry. So here the main important thing is how to find the how to derive exact solution using the obtained invariant subspaces for convex and reaction diffusion equation. Here I can consider the convex and reaction diffusion equation with power law nonlinearity. So we can assume A of u, B of u, C of u are in this form. So then the given convex and reaction diffusion equation 7 reduces to this form. This is a convex and reaction diffusion equation with power law nonlinearity. U admits the one-dimensional exponential space. Easily we can check that the subspace W1 is invariant under the differential operator along with some parametric restriction. So because this h bar satisfies the invariant condition. Then we look for an exact solution in this form, that is u of x comma t equal to a1 of t into e power ax. A is any arbitrary constant. If you are substituting this equation 14 into the equation 13, and system of it's ordinary differential equation. This is a linear. So solving the ordinary differential equation, we obtained a1 of t is this. So then easily we can write the exact solution because a1 of t is known now. U of x comma t are in this form. So similarly, we can consider the dimension n equal to 2. So this is already we discussed in the previous part in the invariant subspace part. So the two-dimensional exponential subspace is invariant under the quadratic differential operator because that g bar of u again in W2. So therefore we can say this linear space is invariant under the quadratic differential operator. Then we look for the exact solution. That exact solution is a combination of this. So that is a u of x comma t equal to a1 of t into the exponential function plus a2 of t into exponential function. So where a1 of t and a2 of t are satisfied the system of nonlinear ODEs. This system of, if you are solving the system of nonlinear ODE, we obtain the exact solution in this form. So similarly, we can consider the another two-dimensional exponential subspace that gives the exact solution in this form along with the some condition, that is a convex and reaction diffusion equation with quadratic nonlinearity admits the exact solution 19. We can construct polynomial solution and a trigonometry solution also. Here I can consider the two-dimensional polynomial space. So that is invariant under the quadratic differential operator. That means convex and reaction diffusion equation with quadratic nonlinearity. We are obtaining the solution or is in this form. Similarly, we can consider the three-dimensional polynomial space. We can write in this form where C1 of t, C2 of t, C3 of t satisfies system of ordinary differential equation. So here I would like to point out that when A of u equal to 1, B of u equal to u, and C of u equal to 0 in convex and reaction diffusion equation, the convex and reaction diffusion equation becomes a Burger's equation. So this Burger's equation admits a two-dimensional polynomial linear space, invariant space, that is this one. So this gives the exact solution in this form where C1 of t and C2 of t are the unknowns that to be determined. So similarly, we can derive the trigonometry solution for convex and reaction diffusion equation. So for this case, we consider the two-dimensional trigonometry invariance of space. That means the cubic differential operator admits the trigonometry space. Then we can write the exact solution in this form. So where a1 of t and a2 of t satisfy the system of ordinary nonlinear ordinary differential equation. The coupled nonlinear system of ODE may not be solvable in general, so I can consider here C naught equal to 0 and A1 of t equal to A2 of t. Under this assumption, we obtain the exact solution or is in this form, so that a graphical representation of the above solution is given here with some parametric condition a equal to a naught equal to 2 under this condition. So this is a trigonometry solution. But the main important thing is this method is applicable to initial value problem or not. Yes, this problem is applicable to initial value problem. For example, here I can consider the Fernberg-Witham equation. So that equation is in this form, along with initial condition u of x comma 0 equal to e power 1 by 2x. By using the invariant subspace method, we this operator admits one-dimensional exponential subspace. Then we can find the exact solution for 23 is this. So this satisfies the initial condition. So therefore, this method is applicable to initial value problem. So here, how we can extend this invariant subspace method to fractional partial differential equation, and why we need to study fractional differential equation. In reality, a natural phenomena may depend not only the time incident, but also on the previous time history, which can be successfully modeled by using the theory of derivatives and integrals of arbitrary order. So here I can consider fractional diffusion wave equation. This alpha ranges between 0 to 2. So when alpha equal to 1, the equation 25 becomes a classical diffusion equation. When alpha equal to 2, the equation 25 becomes a classical wave equation. And 0 less than alpha less than 1, the equation 25 becomes a subdiffusion. It represents slow movement of particles. Alpha greater than 1, then this equation becomes a super diffusion, that is represents fast movement of particle. For 1 less than alpha less than 2, equation 25 becomes 25 studies the intermediate process between diffusion and wave behavior. So hence we observe that the fractional differential equation provides a tool to study both PDEs of parabolic and hyperbolic type process simultaneously. So, and here some examples for subdiffusion and some examples for superdiffusion, diffusion of protein across cell membranes, movement of particle inside a rapidly rotating annular tank. So these are the examples for subdiffusion and superdiffusion. This represents slow movement of particle, this represents fast movement of particles. Here we can do more applications or examples for fractional differential equation. So the Bakley-Torvik equation is one of the example for linear ordinary differential equation. This is arises in Newtonian fluid. It was originally proposed and thoroughly discussed by Torvik and Bakley in 1984. So the derivation of exact solution for fractional differential equation is not an easy task, because some properties of fractional derivatives are harder than the classical derivative. So for example, the derivative of the product of two functions, this is a fractional Leibniz rule, but this alpha is an arbitrary order. But this fractional Leibniz rule is not valid when this rule is true if alpha equal to 1. So similarly, the commutative property is also not valid. So because alpha 1 and alpha 2 are arbitrary. So when this rule is true, either alpha 1 or alpha 2 are integer, or both are equal, or both are integer, then this rule is true. So similarly, the semi-group property is also not valid in fractional case. So when this rule is true, either alpha 1 or alpha 2 are integer, or both are integer, or both are equal, alpha 1 and alpha 2 are equal, then this is equal. This is true. PDs are more complex than the classical PDs. For this reason, there exists no well-defined analytical method analyze them systematically. So here, the Laplace transformation is very effective tool to derive exact solution for linear fractional ordinary differential equation. Laplace transformation of the Kapotov fractional derivative of order alpha. So here I am taking Laplace transformation of the fractional derivative of f of t. So that is in this form. So this is easily we can derive. And this alpha range is between n minus 1 to n. So n minus 1 to n. So totally we need n initial condition for this function, because here the alpha range is between n minus 1 to n. Suppose if I am taking n equal to 1, then the alpha range is between 0 to 1, then this can be written as s alpha f bar of s into minus s alpha minus 1 f of 0. So here the alpha range is between 0 to 1. We need only one initial condition. So here the important thing is that the here classical derivative involving at x equal to 0. So therefore initial condition are physically interpretable. So and additionally the Kapotov fractional derivative of constant equal to 0. So this is one thing, important thing. Transformation of the Riemann-Liouville fractional derivative, but Laplace transformation of the Riemann-Liouville fractional derivative, here we can calculate the initial conditions are involving fractional derivative. So this is a one drawback for this, because no physical interpretation of the values of the fractional derivative at the initial point x equal to 0. This limitation of a Riemann-Liouville fractional derivative is overcome by Kapotov derivative introduced by Kapotov in 1963. Actually, the exponential functions are play a very important role in the solution of the differential equation. So the meta-Lafleur functions naturally occurs as the solution of the fractional differential equation. The meta-Lafleur function is a generalization of exponential, trigonometry, and hyperbolic function. So this function initially suggested by meta-Lafleur in 1903. So after that, Wieman and Agarwal introduced two-parameter meta-Lafleur function that are in the form. So this is a generalization of exponential functions. Properties for meta-Lafleur function, because if you are taking in the two-parameter meta-Lafleur function alpha equal to 1, beta equal to 1, exponential function, and some other cases also here I mentioned trigonometry, hyperbolic, and etc. So here already we know that because Leibniz rule, semi-group property, and commutative properties are not valid in fractional case. So we don't have a method for computing exact solution for fractional partial differential equation. But this invariant subspace method is called generalized separation of variable. So this method easily here we can use for fractional partial differential equation. The following sixth order time fractional nonlinear dispersive positions coequation. So this order of the differential operator is 6. So this f of u, the differential operator f of u of order is 6. So here the dimension of the maximal dimension of the invariant subspace is 13, because 2 into 6 plus 1, 13. So here actually first I'm considering two-dimensional linear space, the two-dimensional linear space. So here I am considering the differential operator f. That differential operator f admits two-dimensional trigonometry subspace if beta equal to 4 gamma minus 4 mu, because it satisfies the invariant condition f of u again in W2, because u in W2. So therefore, we can write the exact solution in this form. U of x comma t equal to C2 of t cos x plus C3 of t sin x, where C1 of t, C2 of t, and C3 of t satisfy system of fractional ODE. So here the invariant subspace method allows one to reduce nonlinear fractional partial differential equation reduces into system of fractional ODEs. So here first I am considering integer case. For integer case, we can easily we can get the exact solution, because this is a C2 of t, because if you are putting alpha equal to 1, this is a second order linear partial differential equation. So easily we can get C2 of t cos x plus C3 of t sin x. This is a integer case solution. Now I'm considering the non-integer case solution. The above system of fractional ODE can be solved through Laplace transformation technique. Then we obtained C2 of t and C3 of t in terms of the Mitter-Leffler function. This Mitter-Leffler function is a generalization of exponential trigonometry and polynomial functions. Then we obtain the exact solution for sixth order time fractional nonlinear dispersive Poisson's coequation in this form. This solution is valid for all alpha. Alpha belongs to open interval 0, 1 closed interval, where k1, k2 are arbitrary constant. Note that for alpha equal to 1, equation 23 is exactly same as integer case. So this is a, because the solution is valid for all alpha. Alpha belongs to 0, 1. So similarly, we can consider the three-dimensional linear space. So the same differential operator here, I am considering the same differential operator admits an invariant subspace, three-dimensional trigonometry subspace if beta equal to 4 gamma minus 4 mu, because it satisfies the invariant condition. So then we look for the exact solution is in this form, where C1 of t and C2 of t, C3 of t satisfies the system of fractional ODE. So the fractional ODE is easily solvable by using the Laplace transformation technique, because this is almost linear one. So here I consider time fractional reaction diffusion equation of second order. G bar of u, this is in this form. So here the order of the differential operator is 2. But however, I am considering the dimension of the invariant subspace is 2. So for two-dimensional case, I'm obtaining two different exponential subspace. So I'm considering the first case, then we can find the exact solution for integer case. For non-integer case, then note that for alpha equal to 1, this solution exactly equal to the integer case. That means the solution is valid for all alpha. Alpha belongs to 0, 1. So here, actually, this method we can extend to time fractional delay PDE also, because already some few one or two papers came in this direction. So here I'm considering the time fractional delay diffusion equation with the source stream. 1 plus 1 dimensional, but h bar of u comma u bar is a order is 2. So here I'm considering two-dimensional trigonometry subspace. This is invariant under the cubic differential operator. Cubic differential operator, because it satisfies the invariant condition. Then we look for the exact solution in this form, that is u of x comma t equal to a1 of t cos root a naught x plus a2 of t into sine root x, where a1 of t and a2 of t satisfy the system of fractional delay ODEs. This is a linear delay ODEs, so it will solvable by using the Laplace transformation technique. But this method we can extend for two coupled system of fractional PDEs and two coupled system of fractional PDEs in higher dimension also. So this method here I am considering the following two coupled system of time fractional PDEs. So this G1 and G2 are operator. G1 order of the operator G1 operator is order is K1 and G2 this is K2. So where alpha 1 and alpha 2 are greater than 0, this is a non-linear differential operator. So here also we can use in a similar way, we can use the linear, we can define the linear spaces. So the similar process, we can find the invariance of spaces. So when we can say this linear space is invariant under the given differential operator, the linear space Wn are called the invariant under the vector differential operator, that is a given differential operator, the component G1 and the component G2. If satisfy this condition, then we can say this linear space is invariant under the given differential operator, vector differential operator. So here, suppose if the operator F admits the invariance of space Wn, then we can write in this form. So here also the invariance of space method allows one to reduce coupled system of fractional PDE into system of fractional ODE. So here Wn is a invariant under the differential operator, given differential operator. Then the given two coupled system of time fractional PDE admits the following exact solution, that is finite separable form where aj of t satisfies the coefficient. So for example, here I'm considering two coupled time fractional nonlinear diffusion equation. So for this diffusion equation, using invariance of space method, we can get more than 10 invariance of space method, but I can't present all the invariance of spaces here. So for example, I'm taking the dimension 2, 1 because this is a coupled case. So for this case, I'm obtaining the invariance of spaces or in this form. So then we can write the exact solution for integer case, that is u1 of x comma t and u2 of x comma t. So similarly, we can compute the exact solution for non-integer case. So here we are getting u1 of t and u2 of t. Alpha equal to 1 in solution 45, then that is exactly equal to the integer case solution. So therefore, the solution is valid for all alpha belongs to 0, 1. So similarly, here we can extend this method to coupled system of time fractional PDEs in 2 plus 1 dimensional. So here this operator involves two space variables, one time variable. The space variables are x and y, so n1 and n2. So this is a given differential operator. So the order of the differential operator can take kp. So here we can consider either Caputo or Riemann, Liouville fractional derivative. So here, in similar way, we can define the linear space is a linear spaces or solution space of the some linear homogeneous ordinary differential equation. So when we can say the differential operator is to admit invariance of space if satisfies this condition. Suppose in case if the differential operator admits invariance of space, then we can obtain this form. Here also the given coupled PDE reduces to system of fractional ODE. This is a finite separable form, so we need to solve this system of fractional ODEs. So here the linear spaces are the solution of the following system of ODEs. And here we can write different type of invariance of spaces for the coupled case in higher dimension, particularly in 2 plus 1 dimensional. So here we can write the functions or the separable form. Here the function of x alone, function of y alone. So here the dimension of the invariance of space first component is m1 n1, and here m2 n2. But here the addition will come m1 plus n1. So two different dimensions, two different kind of invariance of spaces here we can find for the coupled system of fractional PDEs in higher dimensions. So, concluding remarks, similarly, we can extend this method to scalar coupled PD in higher dimension with delay or without delay. The invariant subspace method is called a generalized separation of variables. In this talk, we have explicitly presented that the convection, reaction, diffusion equation admits more than one invariant subspace in different dimensions, which in turn helps to derive more than one different type of exact solutions. The invariant subspace method allows one to reduce time fractional PDE into system of fractional ODE. The obtained reduced system of ODE may be solved by the well-known analytical method. The obtained exact solution can be expressed in terms of polynomial, exponential, and trigonometry function. So this study shows that the invariant subspace method is a very effective and powerful mathematical tool to derive exact solution for integer or arbitrary order scalar and coupled system of fractional or classical PDEs. Book is a very nice book for studying exact solution and invariance of spaces for nonlinear partial differential equation in mechanics and physics. So this paper actually he discussed about the invariance of spaces with quadratic nonlinearity. And this paper, they discussed Bolianon and Jirov discussed about the delay reaction diffusion equation with invariance of spaces. So this is my paper, that is a generalized convection reaction diffusion equation. So this one. So here many other paper is here I mentioned. So this paper is first. This paper is also discussed invariance of spaces and exact solution of certain nonlinear time fractional PDs. So after that, now we extended this method to nonlinear time fractional reaction diffusion equation with the time delay. So these are the references. So and this book are very nice book for studying fractional differential equation, and these 15 and 16. So any questions? Thank you so much. Any questions?
Delegates, if you have any queries, you can ask now. You can discuss with sir. He is friendly, so you can ask anything.
Prakash, how do you in linear fractional differential equations and nonlinear fractional differential equations?
Sir, actually here the linear and the nonlinear fractional differential equation. Actually, in this the same way we can because in classical sense and fractional sense the nonlinear terms are same only, sir. So actually the product of two fractional derivative functions are involving in the fractional in the equation, then we can say that is a nonlinear, sir. That's say in the same in classical way we can say, sir.
Now, from the solution point of view, do you have a definition?
Solution point.
I don't think there is any analogy of linear superposition properties and its validity. When do you say that you have obtained the most general solution of a linear, of a fractional differential equation? Even take just ordinary fractional differential equation.
Yes, sir. So actually,
you have obtained general solution, or what is the definition of general solution? So if you have a second order differential, ordinary differential equation,
then we are getting two different.
you have a solution which contains two arbitrary constants, then you can say that you have obtained the general solution, perhaps.
Yes, sir. Here also we can say, sir, because here in the Laplace transformation technique, 1 minute, sir. Yes, sir.
When the order is fractional,
Yes, sir.
how do you talk about how many independent constants or independent functions the solution?
Yes, sir. Yes, sir. Yes. Actually, suppose my fractional derivative order is, for example, I am taking 0 to 1. That is a linear ordinary differential equation with two terms are involving. Then easily I can calculate two independent solutions, because here if I am using the Laplace transformation technique, suppose my alpha order is n minus 2n, then I need n initial condition. Suppose I am taking n equal to 1, that is 0 to 1, the alpha range is between 0 to 1, then I can get two linearly independent solutions. So this only in the Laplace transformation technique only we can say, but suppose, however, even the linear fractional differential equation also, if involving more than 3 terms, then that is very difficult to solve. So, but only in this point of view only we can say, suppose I am taking the alpha range is 1 to 2, maybe 3.2, that means 1.5 I am taking, then I can get two linearly independent solutions, sir.
Yeah, I think one has to carefully think about all these aspects.
Yes, sir. Yes.
Okay, maybe we will discuss separately. Okay.
Yeah. Yes, sir. Yes. Thank you, sir.
Okay.
Thank you so much.
Thank you. Thanks.
Thank you so much, sir.
Any further queries? Any further queries? I think Prakash, they are satisfied with your presentation. They don't have a doubt because you have in-depth presentation. I also can't able to follow today. I think it is very deep into your research. Thank you so much. Thank you so much, Prakash.
Thank you, ma'am.
Thank you for your mind-blowing talk in the fractional partial differential equation. Thank you so much.
Thank you, ma'am. Thank you so much, ma'am.
Thank you.
Your valuable talk. The feedback and attendance link for this session is posted in the chat box.
Thank you so much, Anna. Thank you so much, Anna.
Oh, okay, great. Thank you. Delegates, please wait. Next session will be start very soon. Please wait. Delegates, please wait. Sorry for the inconvenience. The resource person will come to join very soon. Please wait.
Dear participants, due to the technical issue, participants are requested to take a break for 10 minutes. After 10 minutes, we'll continue. Thank you.
பாலு ஜாயின் பண்ணிக்கலாங்களா பாலு?
Character is the grown and glory of life. This line is probably suitable for Mr. R. Chinnaraju sir. I invite you to introduce the resource person for this session. Welcome, sir.
Good morning to all. Today we have an eminent personality as a resource person, Dr. B. Balasubramanian, Professor and Head and Director for International Programs, Gandhigram, Rural Institute, deemed to be university, who is none other than our alumnus. Having 27 years of experience in teaching and research, he published 244 research papers in the reputed journals with high impact factor. For more than 8 years as a head of the department, obtained several credentials, UGC SAP, DST FISC, R&D project, and NBHM library grants. Under his supervision, 28 scholars have completed their PhD degrees in the field of mathematics and computer science applications. He is serving as a reviewer of many SCI journals and editorial board member of journals. He is editor-in-chief of the journal Modern Instrumentation and associate editor of Neural Processing Letters, International Journal of Intelligent Autonomous Systems, International Journal of Innovative Computing, Information and Control, and Advances in difference equations. He has served as a planning board member, Gobiarts University, Coimbatore, and also a member of the search committee of the Vice Chancellor, Tamil Nadu Open University, Chennai, both under the order from the Excellency of Governor, Chancellor of State Universities, Tamil Nadu. He is the recipient of Tamil Nadu Senior Scientist Award in the year 2018 and Tamil Nadu Scientist Award in the year 2005, and he is one among the 2% in the area of artificial intelligence and image processing. I feel immense happy to invite such a great academician for this international virtual conference. I invite Dr. Balasubramanian to take over the session.
Thank you, Sinraju, and I thank the organizer for inviting me for the today international conference. So I am going to present briefly about what are the roles of fractional calculus in the image processing as well as the neural networks. Sinraju, கேக்குதுங்களா? Hello?
Yes, sir, we are able to hear you, sir. Your voice is clear, sir.
Presentation view ஆகுதா?
Sir, it's visible only, sir.
Okay.
Continue.
Okay. So in the outline of my presentation is fractional calculus and why we need the fractional calculus and fractional derivative, and what are the advantages of the fractional differential equations in the aspect of first in the image processing aspect of the neural networks. In particular, this fractional calculus in recent days is used in many applications. It has been introduced in the 1685 by when Leibniz asked the question to the L'Hospital, whenever the fractional derivative d to the power 1 by 2f by dx to the power 1 by 2 is any physical meaning, then this calculus is nothing but a generalization of the ordinary differential equation and integration of an integer order. Fractional calculus is also known as the non-integer order derivative. So that is why in 1695, when the question was raised by L. Hospital to Leibniz, Leibniz simply answered there will be a paradox in future. Simply, Leibniz answered there will be a paradox in the future. So how this fractional calculus has been improved from the integer order derivative? Just we will see as a mathematician how they formulated this fractional derivative. All of you know what is the derivative dy by dx in terms of backward differentiation. It is limit h tends to 0 f of x minus f of x minus h by h. If it is forward difference, f of x plus h minus f of x divided by h as h tends to 0. So for repeatedly generalizing to second order, and simply nth order differentiation has been written dny by dx to the power n equal to limit h tends to 0 sigma r equal to 0 to n ncr f of x minus r h by h to the power n. Equation 1 represents the nth derivative in the ordinary sense. So now the question is whether this n is an integer could be replaced by the arbitrary any fractions, or instead of n belongs to n, is if n belongs to r real number, is the derivative or equation 1 is meaningful. So that is why if we replacing n to an arbitrary v, then the equation 1 becomes like this, okay? dv y by dxv equal to limit h tends to 0. So the same definition n we replaced by v n arbitrary order. Same. Now the question is whether the NCR instead of NCR, this VCR is valid or not. Okay, if we know the fractional factorial, then definitely the equation 2 is valid. So that can be obtained by using our proper gamma function. For an example, so if we taking dv y by dxv, so it is nothing but the nth derivative represented in equation 2, where VCR is like this, or if we replacing y equal to x to the power k for any k, the with derivative, that is the v is nothing but the fractional derivative, can be written in terms of the gamma function gamma k plus 1 divided by gamma k minus v plus 1 x to the power k minus v. Now we substituting, because v is a fractional order. First we check this validity for k equal to 1, that is for x, f of x equal to x, whether it is valid or not. So substituting v equal to 1 by 2, k equal to 1, what will happen? So this is gamma k plus 1, that is gamma 2 divided by gamma 1 minus 1 by 2 plus 1, or in the denominator we have gamma to 1 by 2. So what is gamma 1 by 2? It is square root of 5 by 2. Okay. So therefore, this derivative half of the derivative of x is nothing but square root of x divided by square root of 5 by 2, or 2 by square root of 5 x to the power 1 by 2. Again, we differentiating this x to the power 1 by 2. X to the power 1 by 2 means k equal to 1 by 2. Okay. So what is it will give only 1. Therefore, if we differentiating twice, with respect to half of the derivative of x, we will have the integer derivative, we will obtain only 1. So that is why this representation of the derivative with derivative where v is a fractional order represented by equation 2 is valid, because we differentiating x to the power of or the x twice the half of the derivative of x, we will get only 1. So that is the integer derivative. Therefore, it is valid. By expanding arbitrary order, nth order to the fractional order belongs to R. First, Cornwall and Litniko, he derived the above derivative. So that is why this is called GL derivative. So expanding this DL derivative, we will have this. So that is why this is called a Cornwall-Litniko differential integral. So what is this definition? This is the definition. Okay. So for example, same. So after his derivative with derivative, fractional order derivative, only in 1847, Riemann-Levelli, they derived the fractional derivative in terms of the following definition. That is called RL derivative. So A is the lower integral, T is the upper integral, V is a fractional power, RL denotes the Riemann-Levelli derivative. That is d by dt whole to the power n of A to T n minus V of negative derivative of f of t, or we simply 1 by gamma n minus V nth derivative of this integral A to T f of x t minus x whole to the power mu minus n plus 1 into dx. Where what is n? N is an integer fractional plus 1, that is an integer number. So if we fix v lies between r, this v, the fractional power lies between 0 to 1, definitely what is this n? N becomes 1. Therefore, the above derivative, okay, RL derivative becomes 1 by gamma 1 minus v d by dt of A to T f of x dx divided by 1 minus x whole to the power v. From the same definition, okay, when n becomes 1, denominator minus 1 plus 1 cancelled. This is nth derivative, therefore 1 minus v. The same equation for fractional power v, where v is a lies between 0 less than v less than 1, the above RL derivative becomes RL derivative of integral A to T f of t is 1 by gamma 1 minus v d by dt of A to T f of x dx into f of x dx divided by t minus x whole to the power v. Here what is RL? Riemann-Levelli. A is denotes the lower integral, a lower bound. T is an upper bound of the integral. V is a fractional order. So now we will check whether the RL derivative is valid for fixed f of t equal to constant. Normally, if we suppose you find derivative of a constant in ordinary sense, what will happen? It must lead always 0, isn't it? If you find derivative of any constant, always it leads to 0. But we check whether RL derivative leads to 0 or not. Okay. Just you substitute for k. 1 by 1 minus gamma, you take it is 1 by, sorry, v you take 1 by 2, 1 by 1 minus v d by dt of integral A. Lower integral you take 0, upper integral you take t. F of t is k, therefore k divided by t minus x whole to the power 1 by 2 into dx. So if we take substitution t minus x equal to u, we will have this or at last we will have, if we differentiating k constant in terms of Riemann-Levelli derivative, we will lead k divided by square root of 5 into 1 by square root of t, where t not equal to 0. Therefore, definitely this is not equal to 0. Therefore, the RL derivative has some flaws or some drawbacks. What is the drawback? If you differentiating a constant, in ordinary sense, it always leads to 0. But in the Riemann-Levelly sense, it does not lead to 0. So this is a major drawback. So that is why this formula derived by the RL sense failed in modeling of some complex phenomena. So we need to redefine the formula. Accordingly, Caputo, he redefined the formula. Just he take the nth order differentiation. You see, where is the 10th order in the RL sense? Okay, this nth order differentiation, you see, dn by dtn is outside the integral. So Caputo simply he has taken this derivative, nth derivative inside the integration. Then he modified the same definition is modified by taking dn by dtn inside the integral. Then he renamed as the Caputo derivative. You see what is the difference between the RL and Caputo derivative? So Caputo has taken this dn, okay? D, what is d? D by dt. Therefore, dn, that is the nth derivative, has been taken inside the integration. Then he named the Caputo derivative. Here see, instead of RL, it is C denotes the Caputo derivative. So now you check the same. When we take f of t equal to k, so you substitute f of t equal to k, what will happen for the first derivative n equal to 1? D by dt of k, d by dt of k is always 0. Therefore, Caputo sense, if we have f of t equal to constant, in the Caputo sense always it leads to 0. So Caputo, he remodified, just taking the outside derivative, nth derivative, into the inside the integral. That is his simple modification. So that is why this Caputo derivative is valid still date for many of the physical models rather than the RL derivative. Even many researchers are also using the RL derivative. Whenever the initial conditions is not necessarily to 0, many of them are also applied for the RL derivative. But the research is only very limited in the RL derivative. So that is why Caputo derivative or Caputo differentiation is very much applied in many of the physical phenomena and applications. Now we will check whether this RL sense or Caputo sense satisfies some of the basic formulas. First, whether it is satisfies the linearity, whether it is interpolation, like this. So first, in a Riemann sense, whether it is interpolated. You see what is the RL derivative. RL derivative, when v tends to n, it leads to nth derivative. When v leads to n minus 1, it denotes the n minus 1 derivative. But in the Caputo sense, you see, because we take the differentiation inside integration, the first derivative v tends to n is same as the Riemann sense. But when v is n minus 1, it is only the difference. The n minus 1th derivative of t minus n minus 1th derivative at t equal to 0. And also linearity is satisfied for both formula, Riemann sense and Caputo sense. Lambda f of t plus g of t, if you apply derivative of RL and Caputo, it leads to linearity. But it is both RL and Caputo derivative are non-commutative. So if we apply v beta, then v plus beta, it is not equal to the beta v. Okay, beta plus v. Therefore, it is non-commutative. And if we taking f of t equal to c, RL sense need not be lead to 0, but in Kapro sense it is always 0. So these are some of the fundamental properties of the RL and Kapro derivatives. Now we will see why we apply this fractional derivative in the applications rather than the conventional integer order derivative. First, because this fractional derivative has more advantages because of non-local nature. The integer derivative of a function at a point which can be approximated using nearby values. Whereas if you go to the fractional derivative, it needs the total history from an initial point. So that is the non-local nature of this fractional derivative plays a vital role in modeling of many hereditary properties and also many other properties in the realistic system rather than the conventional or integer order ones. That is the first advantage because of non-local nature. Second, it is an intermediate process. In many of the physical problems, such as diffusion of fluid flows or fluid flow in the porous media, the integer order derivative cannot be modeled or cannot be represent the physical properties. That is why this type of intermediate derivative is necessary for making a realistic model. Hence, this fractional calculus, due to non-locality in the neighborhood and also the intermediate process is necessary in many of the physical problems, including fluid mechanics or many of the physics oriented applications. So that is why this fractional calculus is very much applied in the research areas, including image processing and neural networks. Now we will see how we apply this image fractional calculus in image processing. First of all, as a mathematician, we must know what is an image. An image is a spatial representation of two-dimension or three-dimensional scheme. Mathematically, it is an array or a matrix pixel. It is arranged in terms of f of x, y. X represents the or column and rows, it always denoted by f of x, y. Or if it represents a matrix, matrix always denoted by a image. But what are the intensity values? Intensity values may depend on the type of images. The first type of image is black and white image. Only if it is a black and white image, the intensity value is only 0 or 1. If the matrix element containing 0, it represents the black. If the matrix element containing 1, it represents only 1. So 1 or 0. So that is the first type of image. Second image is a grayscale image. So each pixel in the grayscale image in the matrix varies from 0 to 255 because the variation in the color between 0 and 1, we have 256 colors that has been represented by 0 to 255. If it is 0, it represents the black. If it is 255, it represents the white. Then third type of image is a color image. It has the 3 bonds values belonging to 0 to 255. What is the 3 bonds? One is RGB, red, green, and blue. So these are the 3 bonds. Each color is varied from 0 to 255 pixel. So you will see the representation of the 3 types of images. You see the image A, we have only 0 and 1. Okay, black color represents the 0 and white represents the 1. If you see the B, the intensity value in the matrix is ranging from 0 to 255. Okay, 77, 70, like this. Okay, so these are the representation. And you see the third is called the color image. If it is a color image, then we have red and green and blue. So these are the three type of bonds. It varies from 0 to 255. So based upon these, we can apply this fractional calculus or fractional derivative for generating a mask function. So what is first of all a mask of an image? Mask is nothing but a two-dimensional signal which is used for filtering the image. The order of an image is always an odd type of matrices, 3 by 3 or 5 by 5 or 7 by 7, like this. The order is always odd because for carrying out convolution, the middle of the mask is required. So that is why it is always in the odd number. If it is an even number, it is too difficult to fix what is the middle of the mask. Therefore, mask is always, the order of the mask is always an odd numbers. So convolution of the mask with a given is given as follows. We explain with a simple example. Suppose we take the input image as the second matrix. A, B, C, D, E, F, G, H, I is a input image. You consider the mask 1, 2, 3, 4, 5, 6, 7, 8, 9 is the second is the mat. We take the convolution of these two, mask and image, by taking like this. Or if we have this A, B, C, D, E, F, G, H, okay, you write this matrix, okay, this mask matrix 1, 4, 7, 2, 5, 8, 3, 6, 9 is a value inside this covered by 0 all over the 9 by 9 matrix. Sorry, here it is 5 by 5, not 9 by 9. Okay, 1, 4, 7, 2, 5, 8, 3, 6, 9. You cover this mask to the zeros outside. Therefore, we will have the 5 by 5 matrix. Now you pass this image. Okay, A, B, C, D, E, F, G, H, I over all these 5 by 5 matrix. First, we move this A, B, C, D, E, F, G, H, I in the 3 by 3 matrix. Therefore, we will have the value of value. What is the value for first 3 by 3 matrix? When you cover A, B, C, D, E, F, G, H, I in the 5 by 5 matrix, we will have this value. What is value of 1? 0 into A, 0 B, 0 C, you leave it. Okay, 1 into E and 4 into F, 2 into H, the non-zero values. Similarly, for value of 2, you just move this to downwards. Okay, then what will happen if we use in the downward? Okay, 1 into B. Okay, you move this A, B, C, D, E, F, G, H, I in the below. Then you have here. Okay, therefore it is 1B plus 4C plus 2F, 2E plus 5F plus 3H plus 6A. Similarly, you move again downwards. Okay, you will have third value. Similarly, you move the right one. We will have 0A, 0B, 0C, then 0D, 1F, okay, and 7F. Okay, that is the fourth value. Value 4. Similarly, you just below down, then again you move this mask to the here in the last most 3 by 3 matrices. Okay, A, B, C, D, E, F, G, H, I, like that. Therefore, here if you move second column, we will have this value, 7th value, 8th value, 7th value, 8th value, and 9th value. So this is the value of, or the convolution of the image with the mask 147258369. So this is a convolution property. So we will get the values. So why we can generate this mask means only to filter the image. So first we need to know what is an edge of an image. What is an edge? When we have an abrupt change in the intensity of pixel, that is called an edge. Or discontinuity in image brightness or contrast. So edge can be defined in these two aspects. Whenever we have an abrupt change in the intensity of pixels or discontinuity in image brightness or contrast, then how to detect an edge? Process of identifying edge is an image to be used as a fundamental asset in image analysis. We could locate areas with strong intensity contrast. So that is the way to find or to detect an edge. So we have edge detection technique. We have 4 types of different edges. As shown in the figure. First is called an step edge, like this our step. Okay. Second is a ramp edge. Third is a line edge. Fourth is a roof, like our roof, house roof. So this is called a roof edge. So what are the methods available to find or to detect the edge? We have, if we go for the first order derivative, the famous gradient methods includes the Robert operator, Prewitt operator, and Sobel operator, and Canny operator. So among those, I think Canny operator is the best method to find the edge. So this is only the first order derivative, okay, called the gradient method. We can also apply for the second order derivative, that is called a Laplacian of the Gaussian derivative. Then gradient based edge detection, we have the magnitude like this, okay. Mod gx in x direction, mod dy in the y direction, 3, 4, and also it has the gradient or opposite of the edge direction is like this. So for example, if we have del x equal to 1, del y equal to 1, the integer order dou g by dou x can be represented like this. The fractional order, just instead of the derivative dou f of xy, we have dou v f of xy by dou xv. Just we represent the fractional derivative like this. Similarly, for the second difference, we have the formula gx gy like this. We can the fractional order like this. Okay? We put the v, the fractional orders like this. So fractional order differential mask for the first difference dx dy is represented by the fractional derivative, that is called a Cronval-Littlecourt definition for the fractional power of f of t. Since the image in 2D array, so that f of t is replaced by f of xy, and the ordinary derivative is turned into the fractional partial derivative, we have the fractional power is v, therefore we have this derivative. Equation number 6 represents the fractional derivative. In the x direction, this is in y direction, therefore equation 6 and 7 can be written in terms of the 5 by 5 mask like this. Okay, you plot f in the 2-dimensional array. This is ij, definitely this is f of I j plus 1, this is f of I j minus 1, this is f of I minus 1 comma j, this is f of I plus 1 comma j. These diagonal elements are f of x I minus 1 j plus 1 and I plus 1 j plus 1. This is okay, you take this is 1 1 f of ij. So this is a left side, right side, this is diagonal side, this is a vertical and lower. So 6 and 7, put the corresponding coefficients, we will get the above table. So along x direction, we set x equal to I plus 1, x minus 1 equal to I, x minus 2 equal to I minus 1, y equal to j. Then 6 can be represented like this. Okay, equation number 8. Similarly, you put y equal to j plus 1, y minus 1 equal to j, y minus 2 equal to j minus 1, and x equal to 1. The 7 can be written as the equation number 9 or like this. Okay, so we have the different type of mask. So if we cumulative these different type of mask in the negative direction, positive y direction, right down diagonal, left upward diagonal, and final mask, we will have the mask is represented by the matrix E. Okay, v square minus v plus 2 by 2. All the, you see, all the elements except this minus 8v, all are the same, called v square minus v plus 2 by 2. So this is the final mask for the fractional derivative in terms of GL derivative. Therefore, we can very well apply this fractional mask to filter the image. So comparison of the has been also given by applying the fractional mask. You see what are the different values of alpha. Here you may change in v is a fractional derivative. Therefore, we change the v values in different way. V equal to 0.2, v equal to 0.4, v equal to 0.6. Instead of alpha, you take it is v. Okay, because we derived the formula in terms of v, or in terms of alpha means alpha square minus alpha plus 2. Okay, v can be the fractional derivative. Therefore, the different type of v values of the fractional calculus, we have the different type of the images by applying the above mask. So you see here, when alpha equal to 1, that is alpha equal to 1 means v equal to 1, that is an integer derivative represented by figure F. You see figure F. How is the figure F? It is very dull image. Comparing alpha equal to, if is A is an original image, if you see the B is somewhat more clear. Clarity is obtained when V value or alpha value is minimum point. If you increasing this fractional value, V equal to alpha equal to 0.4, it is little bit dull. D is 0.6, E is 0.8, and V equal to 1, that is the figure F. So if we dealing the image with the integer order derivative, we will have A and F. A is an original image, F is a image under the filtering of mask of integer order. But if you apply different type of fractional derivative, we have the different type of the clarity in the image. So if you reduce this power alpha or V near to 0, that is alpha equal to 0.2, the clarity is somewhat better. So that is why this fractional theory is very much applied for the filtering processes. So similarly, we can go for the second order fractional mask for dx equal to 2 and du equal to 2. One can deal with the second order derivative. So what is the mask? Okay, mask function is in the x direction, mask function is like this. Similarly, in y direction, we have the mask function is like this. Therefore, we may apply this mask in x direction and y direction very well to deduct what are the crack in the figures. Okay, these represent the cold rack fracture images. So A is an infrared image, B is a reconstructed image, C is the grayscale or gray level transformation image. Okay, so you see for different value, V equal to 0.1, V equal to 0.2, 0.3, V equal to 0.5, 0.7, V equal to 1. So A is a 0.1. You see what will happen? B equal to 0.3. So which is more clear? Maybe for V equal to 0.3, it is more clear than even V equal to 0.1. Even V equal to integer order V equal to 1 means there is no clarity in the crack levels. Therefore, we fix here V equal to 0.3, it is more clear. So similarly, so that is why this fractional mask, either for the gradient first order or second order, is more useful to identify the clarity of the images, or in the filtration process, this fractional calculus role is very much useful to identify the more neighboring informations. And also in the edge reduction, it is easy to lose the image details. To sort out the issues, some of the integer order mask is extended to fractional order mask. And also new pattern of the fractional order differential mask is considered to realize the Kolrak fracture edge feature identification. And also from the local nature, location criteria and location accuracy, which is better than the classical integer order mask. Okay, so that is why this fractional calculus theory or fractional derivative is very much applied to the edge reduction processes than the integer order derivative. Now we will see what are the role of the fractional calculus in the neural network. So before that, we must know what is the neural network. What is neuron? What is neural? What is network? Network is connection between one entity to another entity. So what is neuron? Neuron is nothing but a biological neuron. In biological neuron, even in our brain, we have 10 to the power 11 billion neurons and more than 3 trillion connections that connected by the synapses. So imitating our human brain, we will see what is the structure of the human brain. Okay, this is the structure, biological neuron structure. It has the 4 parts. What are the 4 parts? Important parts is that dendrites. It receives the signals from the other neurons. Soma, it sends the incoming signals to generate input. Axon is the output. And nucleus is called a soma. So based on that, okay, 4 concepts in the biological neural networks. In the biological, you see the structure of the biological neural network is like this. This axon is called an output of the one neuron to another neuron. Dendrites, which receives the input. Nucleus, it is a cell body, are called a soma. And synapses is appropriate weight between one neuron to another neuron. So how many neurons are there in our human brain? We approximately 10 to the power 11 billion neurons and 3 trillion connections are there in our human neural network. So imitating the 4 concept, what is, you consider our computer system. Okay. We need to give some of the input. Why we need to give some input? Because we need to receive some of the output from the computer. So input layer and output layer is more important. So input, why we need to give input? Because we need to get output. So in between input and output, some of the computation is going on in the CPU, central processing unit, that is called a synapse. That is called a nucleus or soma in our cell body. So in between input and output, okay, input, that is a dendrites, that is an input, and also axon through is an output. There will be an interconnection that is connected by the weight. Therefore, the 4 concept axon, that is output, dendrites is an input, and synapses is nothing but an appropriate weight, and soma is a nucleus. So by using the four concept of the biological neuron, the artificial neural network has been constructed. So that is the history, previous history reveals like this. Okay, diffusion of substance in human body, drug diffusion is also phenomena well known to be captured with such mathematical models. The fractional calculus has been employed in the neuroscience to characteristic the generation of action potentials and spiking patterns better, but also in characterizing the biosystems or the vegetable tissues like this. So despite the nature complexity, this biological system belongs as well to this class of systems where fractional calculus has offered many of the accurate models. The fractional calculus also provide a precise model for the description of the dynamic events that occur for the biological tissues. So humans perform complex tasks like vision, motor control, or language or understanding very well. That is why one can build two intelligence machine to try to imitate the human brain. So this is only the 6th generation computing. Up to 5th generation, the expert system played a vital role. But in the 6th generation computing, the artificial neural network played a vital role in modeling many of the physical phenomena. So that is why researchers, not only the researchers, but also for industrial communities, they done research and they raised questions. Is it possible to imitate the human brain into a machine? So that is why in the export system under the 5th generation computing itself, due to the model, or is it possible to imitate the human brain into a machine, they have erupted the automatic teller machine, ATM machine. So that serves some part of the human work is added by that machine, automatic teller machine. So that is only the outcome of the 5th generation computing is called export system. But artificial neural network is entirely different. It is applied in medical fields for neurosurgeons, even for many of the complex systems. This is artificial neural networks played a vital role. So that is why the neurons are some of the basic units in the nervous system. It transmits the electrical impulse to signals. Every neuron is made up of a cell bodies called soma, dendrites, and axon. So dendrites and axons are nerve by fibers. There are about 86 billion neurons in the human body, which comprises roughly 10% of the brain cells. So these are the functions already mentioned. So based upon the human brain are biological neural networks, that is X1, X2, Xn denote the input layer and O is an output layer, and in between that some CPU is central processing unit or some computation is going on in the sigma, where the activation function plays a vital role for the computation. What is the activation function? Where our mathematics is applied. So input layer, output layer, in between that so many hidden layers are there. Okay, hidden layer 1, hidden layer 2, hidden layer 3, whatever may be. So X1, X2, Xn, etc. These are the input layer. Y is an output. Y equal to f of x, where x belongs to Euclidean space Rn. That's simply, if we say a function, mathematics function, what is y? Y equal to f of x. What is x? X belongs to Euclidean space Rn. That's So each x1, x2, etc. xn is appropriately connected by the synapses with weight W1, W2, Wn. That is called a synaptic weight. Then sigma denotes sigma xi wi, where I varies 1 to n. So this function is passed to the activation function. So the activation function contains only our mathematical functions, whether it is linear function or sigmoidal function or trigonometric function, like that. So in activation function only our mathematics plays an important role to calculate the appropriate values for the output. So why this artificial neural networks is necessary? Because even human brain is working in a multi-parallel activities. While listening this lecture, you may dream some things. Yeah, some of the neurons may calculate parallelly or multi-parallelly for so many tasks. Some of the neurons may dream for yesterday events. Some of the neurons may dream the future work. Okay, how to reach a destination, how to go for lunch, okay, like this. So these are all the multi-parallel activities done by the human neurons. That are the classes. While listening, you may think okay, while listening you are also watching some of the emails, internet, and so on. So you are doing some multi in a single task, but our computer system is not like that. If we connected the n nodes in one server, only that n nodes is functioning. It's a single task. What is the task is written by a human, by a programs or codes. So then why this artificial neural network is necessary? So you see some of the representation of the images. You see the image, okay, image of an elephant. How many legs is there? Okay, elephant has always 4 legs. Okay, but if you see human eye, you may represent it may be 5. Okay, so this way got confused like this. Similarly, you see the second image. So really it is a dog, okay, dog image, and also there is some bread which is rolled by around, okay, like this. So we cannot differentiate this dog and also the bread. And third, you see this is a dog, okay, so we cannot differentiate whether it is thread or dog, like that. Okay, you see the fourth image. This is a apple, this is a all. So these difference between the apple and all, the image face of is it is very difficult for a human to differentiate or identify similar type of images. Therefore, this artificial neural network is an efficient computing system which is inspired by the biological neurons. An artificial neural network is an imitation of the human brain. It is a powerful technique to solve many of the real-world applications, and also it has an ability to learn from experience in order to improve their output. Neural network has an ability to deal even for incomplete informations. Some of the edge is not fully completed. By using neural network, it is possible to restructure the image by completing the missing edges. So that is why this neural networks is very much applied for the image analysis and also for the neural networks. So we will directly come for the mathematical structure of the artificial neural network. This is the mathematical structure. Okay, biological neuron. This is an artificial neuron. Trentits, I already mentioned, it is an input, and then nucleus is an activation function, synapsis is an weight, axon is an output. Therefore, this is the structure: output layer, input layer, appropriate weight, synapsis. This is a nucleus is called an activation function. So, if you see some example, how to differentiate the or how to calculate the AND operator in terms of the two neurons X1 and X2. Okay, you have always the bias is always connected. Bias always having the input 1, which has different appropriate weight. So X1 and X2 is connected by the weight 1, and this bias value equal to 1, which has an appropriate weight minus 0.15. Then what is the output A? For if it is the same, okay, input is the same. If we apply the AND operator, then it is 0, 0, 1 is 0, 1, 0 is, or if the input image is different, output is 0, input is same, output is 1. So you apply for the this neural network structure, we have like this, okay, 0, 0, 0, 1, same output. So if we have multiple input values, X1, X2, immediately by constructing this simple type of neural networks, we can have the output. Similarly, you go for the OR operation. Okay. OR operation also, we have plenty of X1, X2. Then applying the simple neuron, we will have the output. Okay. If it is the similar object, which is similar, if it is different, different is nothing but 1. Therefore, we have XOR operation. So, what are the activation function? I already mentioned activation function. Only the mathematical function plays an important role in the activation functions. Okay, what are the activation function? Maybe linear, or maybe Heaviside function like this, or maybe sine function like this, or maybe piecewise linear function, maybe log sigmoidal function 1 by 1 plus e power minus z. Only this log sigmoidal function is applied many of the neural networks because of the nature of this function. When z is very large, okay, the value of z is very large, because exponential is always convergence is very fast. Therefore, and also if we plot the curve, log sigmoidal function, you have the bell shaped curve or uniform convergence is occurred fast, and uniform convergence is occurred only for the log sigmoidal function. Therefore, this log sigmoidal function is taken to be an activation function in many of the neural networks for getting the proper output. Similarly, you can use the hyperbolic tangent function or this multi-layer neural network functions. So in particular, if we have the so many multi-layer neural networks, or if we have in between input and output layer, if we have the one hidden layer, then it is called simply perceptron, single layer neural network. If we have many hidden layers, that are called deep learning neural networks. So what are the drawbacks? Okay, you see in between single layer feedback neural networks. Okay, here there is no in between. This is input layer, this is an output layer. So these are the weight. This is a single layer neural network. Okay, only one layer is there in between input and output. Okay, this is called a perceptron, which is applied. Even still, it is used in our mobile devices as a chip. It reduces the extra echoes. Single layer neural network consists of a single layer of weights where the inputs are directly connected to the outputs. Okay, this single layer neural network has also special name called a perceptron. So you see the multi-layer neural networks. Okay, in between X1 and Y1, these are the hidden layer. Hidden layer here only you have the hidden layer Y1 and Y1, Y2, Y3, Yn are the number of hidden layers. If suppose this number of hidden layers is very high, then it is recently renamed as the deep learning neural network. So deep learning neural network is nothing but an artificial neural network in which the number of hidden layers are high or more. When M is very large, then it is called a deep learning neural network. So these type of the multi-layer neural networks consist of multiple layers, ON, O2, OM, and its structure is denoted by so many hidden layers. The computation units of the hidden layers is done by using different type of activation functions. And suppose in between, it also, the structure is also varied from different type of neural networks. Whenever it is a recurrent neural networks, you see the structure is like this. Okay? Output of each neuron is feedback into the itself as an input. So this is called a recurrent neural network. So why we need this type of network? Recurrent neural networks is required, for instance, modify National Institute standard as a benchmark data or classify some of the digits. Then with a single layer feed for network, you will get a very low accuracy, like around 50 to 60%. So in such a cases, the output is again feed to the input to get the more accuracy. So these are some advantages of the recurrent neural networks. Okay, you see, so in your neural network books, you have plenty of data are available. Are so many literatures they discussed what are the advantages of the different type of neural networks. Even BAM, bi-directional associative memory neural networks is our one of the neural networks. It exactly replicating our human brain. So that is why BAM neural network is applied in many of the applications. So different type of networks is also available. Kogan-Grasberg neural network, then cellular neural networks, okay, CNN. So for those, you kindly refer the literatures, okay, literature which are available in the internet or in terms of the textbooks or in terms of the research papers. Now we will come why this fractional calculus is very much applied in the neural network rather than the integer array. So you consider the discrete case. The equation 14 is one of the neural network structure in which this z of t plus 1 is the state and z of t is the current state. This is future state. Then the difference is denoted by the continuous case as dzt by dt equal to minus c zt a f zt plus I, where z of t is a vector in the Euclidean space Rn, denotes the neuron state vector, and f is represents the neuron activation function, which is nonlinear, and c is any diagonal matrix. So instead of this integer order d z of t by dt, we consider dv zt by dt or d alpha zt by dt alpha. Then we will have the structure represented by 16. So the 16 is the fractional neural network model of the continuous system. 15 is one of the neural network model which consider the integer order. You come to the 16, which is a fractional order neural network. Here alpha is added, where alpha is lies between 0 to 1. So that is the difference. So you consider the fractional neural network 16 with the appropriate value C and A, and we apply the activation function tan h, hyperbolic function f of x t equal to the hyperbolic function tan h t. You see the stability, okay? Nature of the stability for fractional order differential neural network 16, like this. Okay, here alpha equal to 0.74. You see where it is stable. The stability is attained when t is approximately greater than or equal to 7. So it takes either, if we denote t is a seconds, after 7 seconds only, 7 to 8 seconds only, the stability is reached when alpha equal to 0.74. You reduce this alpha 0.65. If you reduce 0.65, you see where it is converges. Convergence is even when small time t is maybe 3 seconds, the convergence is occurred. So even you still reduce alpha value 0.52, you see the stability is occurred with less time. So this is the more advantages. Even still, if you reduce alpha equal to 0.4, we can attain the stability in a very fraction of seconds. We will attain the stability. So nature of stability. If we have any neural network structure, or if we have any mathematical model in terms of the differential equation, there are three important qualitative behaviors. One is the existence of solution. Then whether solution is unique or not. Is stability. Stability is more important. Therefore, these qualitative behaviors, one is existence of solution, second is uniqueness of solution, third is the stability of the solution, are the three important qualitative behaviors for any type of models. If suppose you can model into a differential equation, not only a differential equation, any model, then if there is no solution exist in that model, then there will be no use. If it has more than one solution, there is no use in the application. The system, suppose, is not stable, it has some oscillatory behaviors, then there is no use for the model. Therefore, these three are the more important qualitative behaviors for any of the physical models to apply in the industries. So these are the black diagram. Okay, I think these are all available in many of the books or in the literature. X1, X2, Xn are the input layer. These are the weights. Then weight into inputs. This is the current summation function, sigma Wji xi. Therefore, we can also connect to the electronic circuit models. So even for the continuous model, they can also be represented by like this. Okay, the Sebo circuit model can also be represented like this. Therefore, even for the RLC circuits, okay, we can very well apply this fractional theory to control the capacitor and resistance and also inductor. So that is why this fractional calculus is also very much applied for the analog neural networks and also for the electronic chips, in which these RLC circuits plays a fractional RLC circuits plays an important role to develop the artificial chips to control the system in a more accurate and more perfect way. So that is why this fractional theory in recent days is applied not only for the research community, industrial people, for the usage of many of the practical models are realistic models in a real life. So if we have some of the fundamentals, you may go through these three references and also some of the books, recent books, which are available for the fractional theory as well as the fractional RLC circuits. Okay. If you need some fundamentals of fractional calculus, you may very well refer to the Introduction of Fractional Calculus and Fractional Differential Equations written by Miller and Rose. We have some medical imaging segmentation. You can refer these as some recent conferences, which are all focusing on the fractional applications or fractional order applications in the not only in image processing but also in various fields. They are conducting many of the international conferences focusing on this fractional calculus theory. Many proceedings also available. Therefore, interested people or interested scholars may go through those literature or enrich your knowledge to do your research in future. I leave some of the few minutes for asking questions and interactions. Any questions?
If you have any queries, discuss with us, sir.
Mr. Balu, I have one question.
Yes, yes.
How sensitive your all the networks, neural networks, to that activation function?
Sir, sensitivity depends only on the activation function. If we take the log sigmoidal function, because of nature of the function 1 by 1 plus e power minus z, because exponential function we know always convergence rate is fast, therefore it has more accuracy than we applying for various other activation functions. So it depends only on the type of activation function we choose for the activation functions.
You mean to say, can I say that any network can be made optimized by properly selecting an activation function?
Yes, sir. Yes, sir. It is
Okay.
possible.
Because people say a neural network learning is very efficient only when the activation function has a large dynamic range instead
Yes,
of a
sir.
short one.
Yes, sir.
Is that correct?
Yes, sir.
Okay. So because we are extending this tanh function, we call it as extended tanh. We thought, we are implementing it in a image processing neural network, and we found it.
Yes, sir. It depends only on the activation function. Yes, if you choose activation function involving this exponential negative derivative, so we will get more accuracy and more sensitive result also.
Okay. Thank you. That's what I want to know, because we are trying to do something on that tanh function, activation function.
Okay, sir.
Okay. Thank you.
Thank you, sir. Okay, sir. Any other questions?
Thank you, sir.
Okay, if there is no question, I thank the organizers and also all the participants for patient listening. I hope that these are only the fundamentals or preliminaries for going to or to initiate your research in those areas for image processing and also for the neural networks. I thank the organizers and also all the participants for giving me an opportunity to deliver this lecture in this international conference. Thank you.
Thank you, sir.
Thank you, sir, for your thought-provoking speech. Really, your talk lively maps human brain to the neural network and elaborately pairs the fractional calculus into the artificial intelligence. Thank you, sir.
Okay.
The feedback and attendance link for this session in the chat box. Kindly fill it.
Thank you, sir.
The best teachers are those who show you where to look but don't tell you what to see. We invite such a best teacher, Mr. G.V. Chandrasekhar sir, to introduce the resource person for the 8th session.
Good afternoon,
Welcome, sir.
everyone who is participating in this program. I welcome speaker of this session, Dr. K. Swamasundram, retired professor of Gandhigram Rural Institute, Dindigul, and all the participants on behalf of PG and Research Department of Mathematics of Gobiarts and Science College. I would like to share a brief CV of Professor K. Swamasundram with you. His educational qualifications. So he did his PhD at Indian Institute of Science, Bangalore, in the year 1984. So he completed his MSc Mathematics, MSc Physics at the University of Madras in the year 1976. Completed PG DCM course at Madurai Kamaraj University in the year 1989. Positions held. So he was a professor, the Department of Computer Science and Applications, and as well as in physics and Gandhigram Rural Institute, Gandhigram. So he was a director on the academic side, and he was a registrar and controller of examinations of that university. So to his credit, he is having a teaching experience of 42 years in the Department of Physics as well as Computer Science. So he bears with him a research experience of 37 years, so many articles and books. So to his credit, he has published 182 articles in national, international and national journals. So 42 papers in SCA journals. So he has published 5 books, out of which 2 books has been prescribed as texts in 15 universities and colleges. He has guided 18 PhD scholars who got their PhDs, and he has guided to 30 MPhil students who got their MPhil degrees. So he was a pioneer in introducing computing facility at Gandhigram Rural Institute. So there are a few I would like to mention here. So he has introduced computing programming in Fortran, Global in GRI in 1985. He established Computer Center at GRI in the year 1989. He established Department of Computer Science and Applications in the year 1995. So yes, he is a member in various academic bodies. For this, first he is a member of Board of Management, Planning and Monitoring Board, Academic Council, Syndicate and Senate of GRI, Board of Studies in 12 universities, colleges in Tamil Nadu and Kerala, the academics administration. So he was a Dean, Faculty of Rural Oriental Sciences, Dean, Student Welfare, Head, Department of Computer Science Applications. For 19 years, he was the head of Department of Computer Science and Applications. Then he was head of Computer Science Center for 24 years. So he has visited so many foreign countries. Among them, he has visited USA, Hungary, Australia, Singapore, Italy, Germany, and Thailand. So he has completed so many projects of UGC, DST, and UGC. Among them, UGC MRP 1, DST MRP 2, UGC minor research project 1. So he is a member of so many scientific bodies. First one is a life member, Indian Society for Technical Education, Telemedicine Society of India, annual member, IEE USA, associate member, SCM USA. So his areas of research, medical image processing, image compression, image segmentation, data compression, computational plasma physics, magneto-hydrodynamic surface waves. So these are the only few of his achievements. He has achieved so many things, but since just because of time barrier, I would like to give only a very important of his contributions to this nation. So I request Professor Dr. K. Swamasundram, sir, to deliver
his speech to the audience. Thank you very much, sir. Thank you.
Thank you, Dr. Chandrasekhar, for your nice introduction. And good morning to all of you present who are all on the online with this conference. I'm happy to present my lecture in the International Conference on Dynamical Systems and Subcomputing at Gobiarts and Science College. Yeah, I would like to my PPT. Where shall I put it there? Are you able to see that PPT? Hello?
Sir.
No, sir.
No, okay. Where is the option to share my... Hello? Okay. Use whiteboard, change layout, switch camera. Where is the option to share my PPT? Is it whiteboard?
Sir?
Hello? How do I share my PPT?
Sir, you have present now option.
Which one?
Present now.
Okay. Are you able to see my PPT now?
No.
No?
No, sir. Not it.
Okay. Yeah, present now is able to see that?
Not it, sir.
Empty screen.
If you click present now, you are using laptop, sir?
Yeah, if I am using a laptop.
If you click, no, sir. If you click, you will show whether you can share your entire screen.
Oh, entire screen.
Yes.
Yeah, that's what I put that. Are you able to see now?
No, sir. 1 second, sir. We will see the technical one.
Yeah, I have.
1 second, sir. Gmail add பண்ணு. Calendar phone. So 1 second, sir.
Okay.
Sir, can you refresh the Google Meet again, sir?
Yeah.
Sir, can you now be able to share? Sir, I can't able to hear your voice, sir. Sir, please. Sir, please.
Yeah, are you able to hear now?
Yes, yes, sir, I can hear your voice, but I can't able to see
Okay,
your
screen.
presentations.
Okay. Would like to allow to see the screen. Are you able to see now?
Yes, yeah, yes, sir, yes, sir.
Okay.
Now we can see the presentation.
Can I start now?
Sir, one second. Okay, sir, okay, sir. You can start. Now it is clear.
Yeah.
Sir, you can start, sir.
Delegates, please wait for a few minutes.
Okay, are you able to? Okay.
Okay, sir. Thank you.
Select data copies. Are you able to see now? Hello?
Yes, sir. Yes, sir. See, sir.
Okay, can I proceed?
Okay, sir. Okay, sir. Proceed, sir. Now the screen visible, sir. Okay.
Yes, now it is.
Is it okay?
It's okay, sir. We can see the short
Hello?
view and sir. Yes, sir.
Okay.
Yes, sir. We can able to see.
Okay.
So
You
you can
ask
make it full screen mode.
why compression? There are
Say, excuse me, sir. 1 second. Sir.
full screen.
Full screen mode, sir. Yes.
Wait a minute.
Anushka.
Unmute and then go. Visible? Can I proceed?
Yeah, yeah.
Okay.
Proceed, sir. But we can't able to see the full screen view, sir. It is a small one.
It's small. Let me see where is the option.
Okay, sir. Slideshow, if you go there, I think there is F5 or press F5, sir. It is Windows or not. F5, you know.
Full screen first slide.
So that is not it. Sir, you have play button that's near to that voice. Play button.
Play button. Yeah, I'm just using that.
Yes, sir.
Only through that so there is a play button. I am coming through the play button.
Yes. Your cursor is near to the button. Near to that, sir. Fourth button from there.
Fourth button from because I am using WPS.
Yes, only I have confusion, little confusion, sir. So there only, sir, from the bottom,
near the task bar of that WPS office, we have 6 or 7%. So near to the wall, 100% like that showing us.
Yeah, I'll just make it.
Yes, sir.
There is an expansion because 100% is there, but if I press.
You cannot be able to click that play button is there, sir. No, sir. Down. Down.
Still.
Vertically down, sir. Vertically down. Near to that. Near to that. There is a play button there, no, sir?
Yeah, there is a play button. This is a play button.
Near to that, sir.
Yeah, there is a play button is there, but my screen. Yeah, it is stuck there.
Sir, you can close the
Yeah.
slide transaction first, sir. That is the slide transaction window, side window.
Is that now? Do you get full screen now? No.
No, sir.
Okay.
You can click slideshow there in the menu bar.
Slideshow. Yeah, that is.
Yeah, now this is okay, sir. So one second. Slideshow, click the slideshow in the menu bar.
Now? Is it okay?
Okay, sir. It's now okay, sir. And now you click play button, sir, whether
It is now playing, Can you see the change?
Yes, sir, we can see the big one, but if you click slideshow, whether we can.
It is in slideshow. It is in slideshow mode.
Yeah.
Is it okay now? Okay. Your presentation to everyone. Can you see my screen?
Slideshow on the menu, home, insert design, that slideshow click because the screen is too small when we see in the.
Oh, yes, that's so. Okay, let me see that.
Sir, you can see from the current slide.
From
the current slide, you have a play button in the below the menu bar. Nearest cut, copy, format page.
Yeah, we have the play button is there, but there is fit file to current window.
Delegates, sorry for the inconvenience. Please wait.
able to hear my voice?
Yes, sir. Yes, sir.
Okay, my screen is able to.
No, sir. I think the full screen mode has been disabled again.
Okay, I'll just come back.
So, okay, sir. No problem. You can increase the size, sir.
Yeah, I'll just.
That's 77.7 something it is showing. We can increase the size to 100 so that we can view it.
Hello? Hello? Screen.
Excuse me, sir. Please unmute your mic, sir.
Is it okay?
Yeah, okay, sir.
Okay, right.
Thank you, sir.
Just you have to press F11, sir.
F11.
F11. It is visible in full screen.
Are you able to see F11? No?
No. Control H or Control H.
Control?
Control and H. At the same time, you have to press Control and H.
Control and H. Okay. No,
Sir, are you opening the file in the Adobe Reader?
Yeah, by put Control H.
Sir, otherwise you have to click the icon visible in the menu border plus minus plus and the percentage symbol in the right side of the zone button.
Oh, percentage.
Percentage in the right side of that icon, sir. You have
From
to
the
click,
menu?
sir.
From
Yeah,
menu?
yes, sir. Yes, menu. Yeah, yes, sir.
From the menu, open export. No, from the menu, what? Which one you are telling?
From the menu, that from the left to right, plus symbol and minus symbol and some percentage is there.
From left to right, we have plus minus.
In the middle of the page.
Middle of the page.
So otherwise, no problem. You can continue, sir.
Sir,
Yeah.
I think it is okay now. Screen is
It's okay now, sir.
enough
You
to
can continue.
view.
Share. No, I could not see the plus or minus.
Sir, better it is better than the PDF. Sorry, PPT, sir. It is bigger only, so we can able to listen and view.
Okay, I think I should have tried earlier.
So no problem, sir. We can able to see your screen.
Okay.
Better than PPT, sir. So
Okay,
no
I'll just at least people can see.
yes, sir. We can see. We can see.
Okay. I'm just looking for the single opening.
Sir, no problem, sir. We can continue.
Okay, I'll just we'll go that. I think we have wasted too much of time. Yeah, compression is needed to save the storage space particularly for images. And if you are transmitting across a network, the cost of transmission is huge if the size of the file is large. Therefore, compression achieves two purposes. One, it either saves the storage space or it reduces the cost of transmission of an image. All of you know that everyone uses a mobile phone now. Most of the communication takes place by using images. So therefore, there is a lot of demand to go for developing new algorithms to compress images. I'll present you a few of the basic techniques that are being used to compress image files. Basically, there are two types of compression. One is called as lossless compression. The other is called as lossy compression. In lossless compression, when you compress an image and decompress, it's called as inflate and deflate. That is, after decompression, you will be getting exactly the same data and image as that of the original. Such techniques are called as lossless compression. But the compression that we achieve in a lossless compression is small. For example, if you take a file, an image file, you can compress only up to 0.8%, or 80% can be compressed, or 70%. Beyond that, you cannot achieve. The other type of compression is lossy compression. In the lossy compression, the decompressed data is an approximate value closer to the original data. In the sense, you will not be getting exactly the same data, but a data which is close to the original data. So what you get, if you ask a question, if you get only approximate data, will you be able to see an image? The answer is yes. Still, you can see a reasonably good picture in the lossy compression. For example, if you take all your cell phone cameras have a compressor called as JPEG. Whenever you store your images, when you take a cell phone camera and capture the image, usually it is stored in a JPG or JPEG. JPEG is a lossy compression, but still you can see your images are as good as the original one. So in a lossy compression, the data is very approximate. For example, if you take your passport size photo, you need to recognize a person. That's all you need from a passport size photograph. If you take, for example, a video, if you are watching a cricket, what you need to know is where the player is running, where the ball is going, and you are not much bothered about the quality of the images. So such kind of situations allow you to go for lossy compression. All commercially available compressors are lossy compression because they achieve very high compression, going to roughly like 0.1% of, or it can compress up to 10% of the original image size. So therefore, mostly the lossy compressions are being used, including your cell phone cameras, where whenever you take a photo, you get a JPG. JPG is, or we call it a JPEG, is a compressed image. Now let us look at how compression is done. Every data, when you have a collection of data that represents the image, has some repeated data inside the collection. So compression can be achieved by removing this repeated data or redundant data. The other technique people use to compress an image is by changing the way in which data is stored from an inefficient form to an efficient form. So that also helps to reduce the size of an image. So there is a theory called as theory that measures how much you can compress an image or a given data. So that is being represented by what is called as an entropy. Minimum the entropy, higher will be the compression. So how the entropy is calculated? So the entropy calculates how much the amount of information can be stored in a single bit. So it is given by E equal to minus sigma 1 to n pi, the probability of occurring of the ith symbol, logarithm to the base 2 to the probability pi. So the smaller the number of bits required on an average to represent this symbol. So you cannot go below this value. What is the implication of this entropy is, if you are trying to compress any image, the number of bits required to store a given information cannot be lower than this. So all the compressors try to achieve as close as to this lowest value. There are other measures of compression. A compression is measured by the number of bits required to represent a pixel, or the term used is bits per pixel, or BPP. Normally, if you take a monochrome picture, say usually they use 8 bits of information to represent a pixel. So 8 BPP is the standard value for a normal image. So compression reduces this BPP. Usually those who are using a compressor to compress any image, they measure what's the BPP value. So compression reduces this BPP to as low as 0.1 bits per pixel or even less. For example, if you take JPEG, JPEG can even go up to 0.01 BPP. So we will see these topics at least for the next 40 minutes or so, because your time is constrained. I'll just take very few so that we will save and go as per the schedule. I think Dr. Anandi will be very concerned because we are already lost something like 30-35 minutes. Okay, we will come back to the topic, run length encoding. Variable length coders like Huffman coding, that is used for lossless compression. Coulomb code, Fibonacci code, arithmetic coding, vector quantization, block truncation coding, discrete cosine transform, and there are several other techniques. So these are all the basic techniques which people use for compressing an image. So run length encoding. So in this method, what we do is, suppose given a data, usually we call it as a stream, starting from the beginning to the end. The continuous flow of symbols are taken, and then see how we can compress that. For example, you take in run length encoding, this text, all is too well. So you see in the first word, all, L is repeated twice. So that can be shortened, like, you see the next line A, followed by, we'll say, there are two L's, therefore I put two L's. So it says how many times the count occurs. Next is 2. So is done as such. And then if you take 2, the word containing T, O, there are two O's are there. Therefore, I put T and then followed by the at symbol to represent the count. 2 times are occurring, the O occurs 2 times. Similarly for well, W-E, and then I tell that L occurs 2 times. So if you ask the question, sir, is it compression or inflation? It is an inflation rather, because if you look at the original text, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are only 12 characters, but in our compressed data we have more than 12. But if you take binary images, which are mostly used in digital computers, we will find that binary numbers, either 1 or 0 occurring continuously, is more. Therefore, for binary numbers, the run length encoding is very efficient. In earlier days, when fax machines were there introduced for a real-life problem, you find black and white pictures can be transmitted. In black and white pictures, only binary numbers 1s and 0s are used. Therefore, if you are transmitting such black and white pictures, you will find run length encoding is a very efficient one, and also the cheapest, the lowest complexity algorithm that one can implement to compress an image. For example, you consider the binary string. So that's how, if you see the fax machines or anything that is being transmitted over a network in the computers, only these values are transmitted. Nothing else. It may be a numerical number, it may be a text, it may be even an image, whatever it is, only these numbers are being transmitted across any network, or even storing. It will be stored only like that. Of course, in a physical medium, 1 and 0s are represented electronically in a different form. Now, coming back to our example, we see here if you take the stream of binary numbers, 1s and 0s, if we find in the beginning we have 3 plus 2 plus 3, 5, and 6. There are 6 ones are there. 1, 2, 3, 4, 5, 6. There are 6 ones are there. I think the 5 is wrong. I should have put it as 6 times 1. And then there are 9 zeros are there. I tell there are 9 zeros. And then 4 ones, I put 4 and 1, and then 6 zeros. So if you look at that represented original one when compared to the compressed one, you find that the second one in RLE is very efficient. That's how the compression is done. Still, RLE is one of the methods being used in compression. Now, let's look at this fixed length coders. In representing any symbol, say like A or B or C, or even the numerical numbers 1 to 9, 0 to 9, the 10 numbers, people used to give codes or representation for that. Usually 8 bits are allotted to represent any character. It may be a capital A or a small a or B. 8 bits are, that's the current standard, extended American standard code for information interchange. That is 8 bits in extended ASCII code. If you take A is allotted 8 bits. If you take G is also allotted 8 bits, but the pattern will be different. What is a pattern allotted for A is different from G. For example, you put 7 zeros followed by 1 will represent A. 7 zeros or 6 zeros followed by 1 zero will represent capital B. Like that, these 8 bits are fixed for any number or any alphabets A to Z, capital A to Z, small a to Z, and special characters and the numerical digits 0 to 9. It is an efficient one because when you store the data and then retrieve it back, what you do is you take 8 bits as a group and interpret what it is, either it is a or G or H from the table and then immediately reproduce it. Very good one because the algorithm that you write to read data from a file is very simple. What the algorithm need to do is you take the first eight bits, look into the table, and then reproduce the character. You take the next one, next 8 bits, take the look into the table, and then find out what's the character, reproduce it. So very efficient. You can go for that, but you'll find that is what normally done in your ASCII file when you store your text. That's how your file is made up of A and G, H, or whatever it is. All are allotted the same 8 bits. We call it as the text file that we have is an ASCII 8-bit file. But you'll find this is an inefficient way of representing these symbols. Say A to H or 0 to 9 special characters, whatever it is. Now people have gone for what is called as variable length coders, what is called as a VLC. In a variable length coding, each character is represented by varying number of bits. Say some characters can be given say 2, and few can be given 3, and another can be given 5 or 8, and some characters can be even 12 bits can be allotted or given to represent them instead of 8 bits. That's what is being given. A is given by, say, for example, 8 bits, G is by 5, and then H, N, all are given a different one. How do they arrive at? So the principle is this. The problem in VLC is because even though we say it is very efficient, in VLC, to find where the code representing a symbol ends is a very difficult task. In a fixed length code, no such problem arises. You take every 8 bit, take it to the table, find out what is the character it represents. But if you take one symbol takes 3, another symbol takes 5, and we need to find a mechanism where the code ends for a particular symbol. That is a big issue now. If you are a good mathematician or if you have a intelligent way of thinking, you don't need a very high mathematics, still you can devise. We have published a paper in IEEE transaction multimedia simply by following some common what's called as arithmetic or mathematics that requires only a 10 standard mathematics. We'll see how we are going to do that. So in a variable length coder, Huffman coding is a variable length coder. What is Huffman coding? It is one of the popular methods, or still it is being used. Huffman coding is still being used in many of the compressors because all commercially available compressors are not a single or not implementing a single algorithm, but rather they implement a layer or several algorithms put together as a single system. A JPEG is one such thing where even the JPEG make use of a lossless compression. Huffman coding is a lossless compression, but it's a variable length coder. So what is this principle? The principle is this. Most frequently occurring symbols are assigned least number of bits, and least frequently occurring symbols are assigned most number of bits to represent them. This is the simple principle. So this helps to arrive at or generate a variable length coders. Why? How? As I said, most frequently occurring symbols are given the least number of bits, Instead of 8, maybe you can allot 5 or 6. And least frequently occurring symbols are assigned most number of bits. For example, Z. In English dictionary is occurring less number of times, therefore nothing is lost if you allot 12 bits instead of 8. Still you will achieve. We'll see how it is being done. For example, if you take the English dictionary, it is been found that E occurs the most number of times, and therefore you need not allot 8, but rather you can give only very less number of bits, maybe 5 or 4. We'll see an example later and then show how a high frequency character can be allotted only lower number of bits. Yeah, basic principle of what we know. By using Huffman principle, the total bits required to represent the text can be reduced. What is being done? It is a two-stage process in a Huffman coding. Huffman coding is a lossless compressor. You can compress text and reproduce it. For example, your zip file, a zipper algorithm also makes use of similar to the Huffman coding. Because if you have your text file, that is what you do, commercially available zipper, and you can zip it and then unzip it without loss of your text inside that. And Huffman is one such algorithm. Huffman algorithm is a two-step process. In the first process, what it does is it takes the whole text and then find out how many number of symbols are there and how many number of times each of the characters are occurring. So after doing that, it alerts the code word lengths are therefore shorter for more frequently occurring characters, longer for less frequently occurring characters. How it is being done then? So what, as I said, it is a two-phase or a two-stage process. Scan the text to be compressed and count the total number of characters in that n, and compute the frequency of occurrence of each of the n characters. For example, if you take an English dictionary, the distinct characters can be only 52. Uppercase A to Z, lowercase A to Z, there are 26 plus 26, 52. If you have got, say, another 5 special characters like dollar, plus, minus, then we have 52 plus 10, say, 62. So the n becomes 62. What we do is you find out how many number of times each of these 62 characters are occurring. That is the frequency of occurrence. So, and then after that, sort the characters based on the frequency count. For example, E occurs most number of times, and then Z occurs. You just go and arrange the frequency count and the corresponding characters. Build the code tree based on the prioritized list. In algorithms, you all know, in representing data, we have the what is called as priority queues are there. You can create queues, and using these, from these queues, you can again take up by using certain algorithm, dequeue them, and then create new nodes, and then finally, from each of these nodes, you will get only one single tree. So after creating that, perform a traverse of tree and determine code words for each symbol, scan the text again, and create the new compressed file. So after finding the frequency of that, we will be creating a tree. So for that, what we do is we create a one prioritized queue. You arrange or sort out all the characters in the decreasing, increasing frequency count. Using that, you build up a tree. It is like a map. When you go to a new place, in order to find out new places around, you use the map. In a similar way, the Huffman tree helps you to generate the code word for each of the characters. Let's see, therefore, the second stage, this is the first stage, and the second stage, it takes up the scan, that is, it takes up the original text, scan the text, and for each of the text from the tree, you can allot, or from the table that you have generated, you can allot codes for each of the symbol. Well, just I will show you an example, and perhaps that will give you an idea how it is being done. You take the simple text, airy eyes seen near lake. So this is the given text. We want to now compress it. So what we do as per our algorithm, you find out how many distinct symbols are there. Yeah, scan the original text. What characters are present? Airy, E or I, and then space. Space is also counted as one of the characters. So there are 12 distinct characters in this sentence, including the full stop and the space that we see here. And then how many times each of them occur? So E occurs one time. So this is a frequency count table. A small e occurs 8 times, or occurs 2 times, I occurs 1 time, space occurs 4 times, y once, like that. All the 12 characters have this frequency count. Now what we do, you arrange them in an increasing order of frequency and then create a prioritized queue. So create a binary tree nodes with character and frequency of each character. Place nodes in a priority queue. The lower the occurrence, the higher the priority in the queue. That's how the queue is being counted. Now look at this. From the frequency count, we'll start from the lower frequency one occurs at the beginning, and the highest frequency is occurring at the end of the node, end of the queue. So now we have that priority queue here, starting from the lowest value and then in higher and higher last value. Now you construct it. After constructing it, what we do is from the priority queue, you take the least frequently occurring one, you take it, create a node. For the node, the sum of the two values becomes a node value. Yeah, from the queue, what I do is just take E and I. So E and I, the sum of the counts becomes a node value. And after doing that, we insert back into the queue, priority queue between, it may be here, but the procedure is we adapt is between the lowest and the highest one available there, therefore insert here. Now repeat it. You go to your priority queue, you take the first two here, you form another node. So Y and L we have, and then again the sum of the frequency becomes the node value, insert at this point. Okay, I will insert it here. So go on, repeat it. So the next we'll do, take K and I, which occurs once, and then again insert here. Now R and S occurs 2 times with the frequency. Again take, now if we make a node, it will have a value 2 plus 2, 4, and then 4 is inserted here in this queue. So it has come. Now N and A, you take the 2 nodes from the priority queue and repeat it, and you'll find, so you'll get ultimately a single tree. Well, this is the Hoffman tree. Now we have built the tree from that. That is the first stage of the Hoffman algorithm. Now, so after enqueuing this node, there is only one node left in the periodic queue, this one. Now, dequeue the single node left in the queue. This tree contains a new code words for. So what we do is, this is the map for generating the characters. Here is I see near leg. There are 26 characters. Now what we do is, we'll develop a algorithm or a procedure. What is the procedure? Encoding the traverse the tree for codes. Perform the traversal of the tree to obtain new code words. In the tree, when you move in the left, you generate 0. When you move in the right hand side, you generate 1. That is the rule that we follow. Now, for example, if you start from the node, you go left, again left, that is 0, 0, 0, 0. If you put 4 zeros, you end with capital E, the leaf node. See here. So therefore, 0, second 0, third 0, fourth 0, we reach capital E, the character. So the E recurs or E can be represented by the 4 binary zeros. Now, if you come down again 0, 0, 0, instead of right, because already we have traversed to that, and then 1, you reach I. So I needs 3 zeros followed by 1. Or if you want to get I, you need to represent only by 3 zeros and 1. Similarly, if you come here, 0 and then 0, you move in the right because you already exhausted this. 0, second 0, and then 1, and then 0, you reach Y. See this word. So you are able to get this. Now, in the same way, for example, you take this case 0, sorry, this is 1, 0. If you have that, you reach E, small e. You just see here E, you need to represent only 2 binary bits or record. Similarly, space records only 3. So what you learn from this is, you see here 8 occurred, E occurred 8 number of times. That code you need as per the Hoffman tree is, or Hoffman algorithm is, you need only 2 binary bits to represent it. Whereas the others need at least 4, because simple problem, we have only 4 codes or 4 binary bits are required. Had we taken more number of the characters like in the English dictionary, including all these uppercase, lowercase, and special characters, we might have got even higher frequency codes. For example, Z might have taken 12 bits instead of the usual 4 bits. Now come here. Now we have, using the binary Hoffman code, we have generated the codes for each of the characters. Now this is the first stage is over. Now we go for the second stage, where we will compress the given file. We take the original file, scan it. Yeah, Eric, eyes are seen. First we will scan the original text E. As you can see here, E is to be coded 4 zeros. Therefore, I'll put 4 zeros are here. Next, small e records 1 0. We have seen already 1 0. Therefore, if you take this, the whole, each of the characters, you allot the binary code. Now we have done the compression. What we have done, so we have converted the given code to a binary compressed file. So the encoded data and the tree together forms a compressed file. So when you send a compressed data, not only this compressed data, but you also need to send the map or the tree. Without the tree, you cannot reconstruct. Therefore, this is an overhead. This is the actual data. This is the compressed data, and this Hoffman tree both form the compressed file. It will be sent from the source to the destination or the receiver. So the receiver will get this tree as well as the data and do the reverse process. Now, before we go, let's see what compression we have achieved. What is the compression done? 84 bits to encode the 26 character text. So originally we were using 84 bits to represent the 26 character set. Now after compression, namely ASCII would take, had it been, we have taken only 84 bits to represent this 26 character text. Whereas if you have taken, normally, as I told you in the beginning, all characters are represented by 8. Therefore, 8 into 26, you might have taken 208 bits to represent the same file. So see here, instead of 208 bits, we are taking only 84 bits. This is the compression we have achieved. Now, coming back, suppose if you have given a large text, even your compression of the number of bits you have saved will be more. Here only 208 minus 84. If you take 90, so almost 50% we have reduced. More than 50% has been reduced. Namely, if you have got a 2 kilobyte of original data, we have reduced to 1 kilobyte of data. That is a compression we have achieved. Okay, now we go to the next stage. Having compressed this data in Hoffman code, how you are able to get it back? So how does the receiver know what codes are what the codes are. The tree constructed for each text file considers the frequency for each file. Big hit on compressor, especially for a tree. Okay, leave that, we'll come back. Okay, now how we do this decompression is done. What you do is, as I said in the beginning, when you send the compressed data, it contains two parts. One is the compressed stream of binary bits, and then the binary tree. This is essential, both are essential to reconstruct the image. What you do is feed this stream of binary bits into this the Hoffman tree. So what I do is I feed it. So what you need is you starting from the beginning, you feed the values into this Hoffman tree until you reach the leaf node. This is called as a leaf node in a tree. So now let's start from here, what we get back. So you feed 0. When you feed 0, you go in the left, and then again left, and again left, and again left, 4 zeros. So you get E. Once you reach the leaf node, you stop your process and generate. At the leaf, you have the E and reproduce E, and then start from the beginning again. So 1, therefore go in the right hand side. 0, go in the left hand side. So you reach E, you produce small e. Like that, you see here, if you do that, you'll get back exactly the same text which you have compressed. That's how the Hoffman code works, and it produces a lossless compression. So one of the problem, or many of the problem associated with the Hoffman coding is that text has to be processed first, and then generate the code and compress it. But for online applications, as I said, it's a two-step. Before compressing the file, the whole file is to be given to the Hoffman code. Only then it can find the distinct characters in that number 1, and only then it can find the frequency of occurrence of each of the characters. So that means the file is to be given first, complete file. But for example, if you take the online text processing, wherein someone is speaking like me, so when the text is streaming out, Hoffman code cannot handle that because it needs a complete file. But in an online transaction, an online text transmission, that is not possible. Therefore, in such cases where the online text is being processed, Hoffman code will not work, but there is a variation for that. Hoffman code is modified so that it can handle the streaming online text can be handled in that. So anyhow, Hoffman is the code, is the first lossless compression, but still it finds some uses in the lossless compressors. So we have other codes called as prefix codes, which are all used for compressing the images. So prefix property requires that once a certain bit pattern has been assigned as the code of a symbol, no other code should start with that pattern. As I said in the beginning, we are assigning a bit pattern for each of this symbol. The prefix codes, what they say is, once you give a pattern for a particular character, it should not be repeated for other characters, because it is quite natural. If it is repeated for other characters, then it cannot be used for compressing files, so that distinct characters cannot be extracted from that. So what's the property? The prefix code, a prefix code is a variable size code that satisfies the prefix property. Okay, there is a code which is a prefix, used as a prefix code, unary code. What a unary code says? The unary code of a non-negative integer n is defined as n-1s followed by a single 0, or n-1 zeros followed by a single 1. For example, that this is 1 in the code 1, namely the n-1s followed by a single 0 is, we take from here 2 n-1 ones are there followed by a 0, or n-1 0 followed by the 1. 3 is n-1, there are 2 ones followed by 0, or in the code 2, 2 zeros followed by 1. Similarly, for example, 5, 4 ones followed by 0, or in the code 2, 4 zeros followed by 1. That is n minus 1 zeros followed by 1. This is called as a unary code. Yeah, column code is another one which using which you can compress the data. It is very what is called as, it needs only a common sense. Suppose if I ask you, can you compress 25? It is quite interesting. So how will you compress 25? So if you want to compress 25, one of the simplest form is you divide by 5, you can get only 5. In the sense, you take any number in the given set and divide by 5, keep the quotient alone. If you've got a fraction and it's not a problem, we'll see how it can be handled. So the problem is, suppose you've got numbers having like 25, 35 or 85, you divide by 5 by a common divisor and then take the remainder and quotient, store them. That also is helping you to reduce the size. So in a column code, what you do is, given the n, subtract 1 and divide by a divisor. Then you divide, take a divider of your choice. The choice depends on your application. You can take the divisor as a 3 or 4 or 5, whatever you like. It is up to the user and up to the application that is being under consideration. So you find the quotient by dividing the number and take the remainder and then do it. So represent the quotient by a binary, and this is by a unary code. So column code consists of two parts. The first part is the value q plus 1 coded in unary, and the second part is a binary value of r. So for example, if you take a divisor d equal to 3, it produces 3 possible reminders. So when you divide any number by 3, you will get a reminder. So that will be less than or equal to less than 3. Therefore, the reminders will be 0, 1, and 2. So the 3 are coded, were given a special codes, 0 for 0, and then 1 is given a pattern of 1, 0, 2 is given a pattern of 1, 1, and are given in the table. So for example, we'll see that later. Coulomb code for reminders D with the reminders D equal to 3 and 4 are like this. So you take a D equal to 3, the 0 for both of them. 0 is represented by 0, 0. 1 is represented with a divisor 1, 0, and with a divisor D equal to 4, you have 1. And for 2, with the divisor of D equal to 3, we have 1, 1. For the other, we have 1, 0. Because there are only 3 for D equal to 3, we have only 3 representations. For D equal to 4, we have 0, 1, 2, 3. There are 3 reminders. These are all the prefix codes. Now you take consider value. Now we'll take an example and then see how it is being compressed. Let D equal to 3, then Q become 2, and then R. This is a simple thing. It becomes code Q plus 1 in unary. Unary code for 3 is 1, or 0. Code for the remainder R equal to 1 in binary is 1, 0. Therefore, Coulomb code or compressed value is 1 and 0, and then followed by 1, 0. Now, how you decode it? You reverse it, you will get back the same 8. Okay, now we are running short, but we will go back to the how an image is compressed. I will just show you a method. Yeah, because I'm skipping this. At least one method I can just show you. Yeah, we'll come back. In fact, I should have told you in the beginning itself how an image is compressed. I'll just see that, as I told you, any image is represented by a binary array of 2-dimensional numbers. This is a black and white picture. Each of the value, for example, if you take the nose, the digital image consists of sampled values. Sampled value means an image is a continuous one in nature, and you cannot represent a continuous value in a computer. And therefore, people sample them in x direction and y direction, and for each of the grid, they take how many samples they take are being represented. For example, in this nose of the baby, we have divided this. This consists of 10 rows and 10 columns. Namely, 100 points are used to represent this nose. So each of the pixel or the pixel element or dots, it is called as. So in this x direction, these values shows in a monochrome a value 99, 71, 61. So what I need to tell you is each of the sample point are represented by an intensity value called as pixel value. Pixel represents what is called as pixel element. So in a monochrome black and white color, we have a value starting from 0 to 255. If you ask how you get this value 255 in a binary number system or a digital computer, a pixel element is represented by an 8-bit. So once you have an 8-bit, you can have different patterns equal to 2 power 8 bit patterns are possible. That is 2 power 8 equal to 256 patterns are possible. Therefore, the value, if you have got any black and white picture, then the intensity values will vary from 0 to 255. Why people take this monochrome? If you ask the question how people will deal if it is color image. A color image is represented by several models. One simple model is a red, green, blue model, in which each of the color can be represented by 3 different colors: red, green, blue. By mixing these red, green, and blue, you can generate any color. And therefore, in a color image, instead of this simple 2-dimensional array of numbers, we will have three layers like this: one for red, another for green, another for blue. So it is a question of processing the 3 layers together and then compress it. And therefore, if you have got any theory that can be used to compress a single layer, that can be extended to the 3-layer or color pixels also. For simplicity, people usually take a monochrome, a single layer or 2-dimensional array of numbers, and then show how the compression is working. So this is a pixel value for this black and white. And now we'll go there, proceed with, and then see how a digital image like this are being compressed. I told you in the beginning, in an image, image is not transmitted as an image. Actually, it is transmitted or stored in terms of these values. These values are actually basically stored in the form of a binary. For simplicity, it is given with decimal numbers. So compression like that, to give the input image, compress an algorithm, compress the file, decompress and get it back. So there is one simple algorithm to compress an image, what is called as block truncation coding. The name comes because the given image is divided into an n number of blocks of a particular size. For example, usually into 4 into 4. For example, you take this image, each block, though it is higher end, I will divide them into 4 and 4, 4 into 4 size pixels, and each of the block is being processed and compressed. So that's how the name comes as a block truncation coding algorithm. What you do then is, if each of the block, now we have 16 elements are there, find the mean of the 16 elements, find the standard deviation of this. What you do then, and if what you do is construct a bit plan, all the values higher than x, the mean value x, will be taken as 1. All the values which are less than this will be taken as 0. So therefore, you will be generating 16 binary bits, either 1 or 0, and we will be storing the binary bits 1 and 0 as a bit plane, plus what you will be storing is the mean value and the standard deviation as the compressed file. So if you take a block of 4 by 4 pixel, what we will be doing is 16 bits, either 0 or 1, plus the mean value in 8 bits and then another standard deviation will be sent for one block. You repeat for all the blocks that forms the given image. This is an example. This is one block. You find this is the value. You find the mean value. Mean value is 98.75. Standard deviation is 92.5. So what you do is, for all the values which are all above that, you put as 1. 121. Is it greater than the mean? Yes, you put 1. 114. Is it greater than 98.75? Yes, 1. 56, is it greater than? No, you put it as 0. Therefore, from this block, what we generate is a bit plane. This is called as a bit plane. 16 binary values, either 1 or 0, plus we'll be sending this 98.75, the mean value, and the standard deviation. This is the compressed data. We repeat for all the pixels. For all the blocks, we have divided. This is block 1, 2, 3, 4, like that. And then after compression, what you do is, how do you decompress it? So decompression makes you that out of the 16, you find out how many number of ones are there, take it as P, how many zeros are there by Q, where P and Q are the number of Q zeros, P represents the number of zeros in the bit plane, and Q represents number of ones in the compressed bit plane. Here, number of ones is, total number of ones is P, total number of zeros is Q. And then what you do is compute the Q values by making use of the standard deviation and the mean value that is being sent along with the file for compression. The H equal to X bar plus sigma into square root of P by Q, you get one value, and L value you get X bar minus sigma into square root of Q by P. You get two values. What you do then, and using these two values to reconstruct the image. So for the previous example, we have H equal to 204, L equal to 1 by 4. Wherever there is 1, replace with 204. Wherever there is 0, replace with 17. You get your reconstructed image. So that's how the decompression works. So in a block truncation coding, you will be achieving instead of the 8 bits per pixel, you'll be needing. This is the calculation we make. How many bits? As I said, the BPP is calculated. So the total number of bits required for a block size 4 is mean is 8 bits, standard is 8 bits, bit plane 16. Therefore, originally, otherwise, suppose if we have taken, we might have needed 16 bits will be needed, but whereas we have that, there are 16 pixels over there, 8 for mean value, 8 for the standard deviation, and then 16 bits. Therefore, there are 16 pixels in that image block because we have taken 4 by 4. Therefore, what you get is the bits per pixel is equal to 2. And then what is that we have done? We have done, instead of 8 bits to represent a pixel, we have used only 2. Namely, we have reduced 6 bits in this. That's the achievement we have made. Therefore, the compression ratio is original size divided by compression size equal to 16 pixels into 8 pixels divided by 32 bits equal to 4. Therefore, in a block truncation coding, you will be able to compress 4 times. Namely, if you have got a 4 kilobyte of image and you can compress it to 1 kilobyte. Now, what are the results? This is an uncompressed Lena image. Usually, people use the standard images whenever they develop a new algorithm, apply it on a standard image. People throughout the world make use of it and then do it. How many uncompressed image size? 256 into 256. Each pixel taking 8 bits. Therefore, 5,24,200 bits are needed. In our compressed size, you need only 65,500 bits are needed. Namely, as I said, it will be 4 times compressed. And now, if you ask a question, sir, when I decompress it, will I be able to get back my image which is recognizable? Yes, you can. This is the decompressed image file. So reconsider an image. I think you will be, if you see, there is not much loss unless you go pixel by pixel, and that's how you are doing the compression in a block truncation coding. So there are other variants are there, but I will stop it here because of time constraints already 1:30. Yeah, if you have got questions, yeah, I'll go to the end and then.
Sir, you continue.
Yeah, this is the reference fundamentals of data
Sir, you
compression.
can continue.
Because it is already 1:30, Dr. Anandi.
No problem. We can change the session to 2 o'clock, so no problem.
How much time I can take more?
You can take 10 more minutes, sir.
Okay.
So I think within 10 you can complete because few slides are left.
No, but we have an evening session that will disrupt.
No problem, sir.
Okay, I will just come back maybe for mathematics people that will be of some use. Okay. Yeah, I'll just take another method, what is called as vector quantization. So in the previous one, yeah, this is the previous one, the block truncation coding. We have seen this reconstruct image. Absolutely, you are able to get back an image which is recognizable. So in this block truncation coding, what we have done is we have quantized. That is, changing a particular value to another value. A range of values into one value called as quantization. We have done each of the pixel value, modified it, but there is another method called as vector quantization method. The name itself says something vector is being used. Yeah, in vector quantization, the vector is used as a quantizer instead of single value. In the block truncation coding, we have used only one, for each of the value we have made one quantization that is manipulated each of the pixel. Whereas in this vector quantization, what we do is we take a collection of quantities which we call as a vector and represent the vector in a different unit, that is by a different vector quantity. So that's why the name vector quantization comes in. Let's see how the vector quantization works in. Almost in the vector quantization also, we divide a given image into number of blocks, right? And for example, the same 4 by 4. So let's say the Lana image, we take one block, the one block 4 into 4. So we make it as a linear array. So we have a vector. So 99, 1. So just you take 99, 105, 110, and then 112, and then 98. So we make it as a vector. Now what we do is, we take all such vectors from the blocks that we generate from the given image. Now, for example, in this, if you take 256 into 256, if you divide into 4 by 4 element vector, we call these as a training vectors. So we have number of blocks are there. Each block we take it out 4 into 4, divide it, and then construct into a linear vector like this. So we'll be having, so we call it as a training vector. Then what is the principle in compression use, or the principle for compression use in a vector quantization? What we will do is, for example, you take, there are a number of ways to do that. For example, you take first 4, 1, 2, 3, 4. Okay, what is the representative vector for all the 4 vectors? See, that means 4 into 64. All the 64 elements are represented by a single vector. It is like when you have a classroom and you have a class representative, he will represent the whole class, all the 45 students or 50 students. Similarly, we have 4 vectors are there. We select by using some algorithm. You can develop your own if you wish. Quite interestingly, there are a lot of research is going on. So you take the first 4 elements, 4 vectors, and take a sample vector out of it. How do you generate a sample or representative is using a particular algorithm. We will see some of the algorithms. You will learn how you can generate your own algorithm if you are a scholar dealing with image compression, or at least you learn if you have got your colleagues, you can tell how this vector quantization works. Okay, now we will have this m into n size quantity. The training vectors are there. Out of the training vectors, yeah. So what is the process here? As I said, VQ, vector quantization, is a two-pass method. In the first pass, it finds a vector quantization where one representative vector for a group of training vector is found. Namely, as I said, you take the first four. For the first four, you find out one representative vector which can be very close to each one of the four. Next, this representative vector is called as a code vector. So we generate code vector, namely for every four you generate one. For example, if you have got 16, for 16 vectors, we'll have a representative. If you have 16 divided by 4, we'll have only 4 representative vectors. These 4 representative vectors are called as the code vectors. So if you have got say 96 divided by 4, you get, so you have 24 vectors are there. So for 96 training vectors, you will have only 24 representatives. These 24 vectors are called as the code vectors, and the collection of 24 is called as a code book. So in a vector quantization, the whole problem lies, or the whole problem, or the whole core of the problem is find an algorithm that will generate the code book. So in vector quantization, code book generation is an important one. So for that, people can develop their own algorithm and generate the code vectors. So after code book, after generating the code book, what you have is the second pass. You have now one code book is with you. Now you have your image to be compressed. You again divide them into number of blocks, and each block you generate one training vector. You take the training vector or compare with the code vectors, and then find out, because we have each vector has a value, you find out which of the vector is very close to in the code book, which of the code vector is very close to the testing vector. You take it as that value, because now all of the vectors will be having a value from any one of the code book vectors. So if you've got a code book that contains, for example, only 16 vectors, these are the 16 vector values, we'll just assign them index. So vector index will be assigned. So the whole image will be taken and will be taken index. For example, you take the first block, find out which is the closest one among the 16. Suppose it matches with 5, you put the index in the compressed file as 5. You take the second block and then again convert into a vector, and then test the vector which is close to the code vectors. Suppose it matches with say 8, you take the value 8 into your compressed file. Therefore, if you have got to say, for example, 4096 vectors or their blocks are there that represent image, we will also have 4096 values, but these values will vary from 1 to, for example, if the code book contains only 256, a value between 1 to 256 will be there. Now this also achieves. So this is how a vector quantization works. In the first phase, code book generation, we have a code book. As I said, you divide the whole image into blocks. Each of the block is converted into a training vector, and from the training vector, for either group of 4 or a group of 8 or a group of 16, you generate a code vector. The collection of such vectors are called as code book. That is phase 1. In the second phase, you take again the image, you divide them into the same number of blocks. You find out which the vector which is very close to that, and generate the code indices for that. and then send to the compressed file. Like that, you just take all the vectors, input vectors taken from the given input image, compare with that, find out which is the closest one, and send the indices. Now the indices and the code book will form the compressed data. Therefore, the sender will send the code book and the indices, compressed indices, and to the sender. The sender will get the indices like this. That's, we have the indices and we have the code book. So you take the first indices and then look into that 16. Yes, reproduce the value. That's how the decoder works. Now you'll be able to get back. Yeah, the same block. As I said in the beginning, you'll be getting the same thing being represented by a code book. You'll be getting back the same original, that is reconstructed image block. You repeat it for all the blocks that you have, you'll be able to get back your image. But the only thing is the vector that represents the reconstructed image will not be the same as the original, but it is very close to that. So that's why we call the vector quantization is a lossy compression. Right? So there are algorithms. You can read Lloyd algorithm, how you can generate code book, Linde, Busso, Gray, and then there is an algorithm. This is also a simple one. You don't require much of mathematics, and then you can use this for vector quantization algorithms. Yeah, I'll just take this discrete cosine transform, though Dr. Anand gave me 10, at least within 5 minutes I will complete. So discrete cosine transform is purely a mathematical tool. So there are algorithms which we have seen in literature, and even some of those people who are working in compression or even in other domains, wherein you generate some mathematics which will work only for that case. If you want to enhance or change it to a higher scale, it is not possible. But whereas if you go purely mathematics, if you use a pure mathematics, and for such problems, you'll find, though it may not fit, but going or scaling up to different levels is very, very easy. Transform is one such a mathematical tool, originally demonstrated by 2 or 3 people.
Participants, please wait. Sorry for the inconvenience.
Delegates, sorry for inconvenience. I think Sir has a technical issue, so he can't able to continue the session. So I thank this professor for his in-depth explanation of compression. Even though we are mathematicians, we are unaware of maths used in compression. Really, it is useful for a young researcher for their research. Thank you so much, sir. Sorry, delegates, he has a technical issue to join in the session again. So we will send the PPTs of all the invited talks to you. So don't worry. We can have a break, and those who are having presentation, it will be scheduled at 2 o'clock itself. You can join. After presenting, you can leave the meeting. Okay, and you can join again for the valediction at 3:30 p.m. Okay, and you can fill the feedback form which has been posted here. If you have any queries, you can ask now regarding the parallel presentation session or the valediction. Have you all received the link for presentation?
Yes, ma'am.
Okay. Okay. The order of the presenter will be the order of the manuscript ID provided in the presentation schedule. So that order will be followed. Okay. The co-chair will inform which ID should be presented first. So no problem. So you be on this line itself. The presentation schedule 1 can be line on this link itself. The second, for students, you can go on to the second link that already I think mailed in the morning. Okay. For the paper presenter scheduled in the session 1 can be online on this link itself. Those who are students listed in the second session can move on to that link. Okay. Thank you.
Hello, sir. Nandagopal sir, Muthukumar sir. Good afternoon, sir. Sir, Nandagopal sir.
Hi, sir.
Sir, good afternoon, sir. Muthukumar sir, good afternoon.
Good afternoon, sir.
Shall we start, sir?
Sir, we can start the session.
Okay, sir. Okay, sir. First we call the manuscript 13, sir. Then after, as usual, the serial number, sir.
Okay, ma'am. Okay, sir.
Okay, sir. Okay, sir. Thank you.
Good afternoon to all. The paper presentation session starts now. I invite Mrs. P. Uma Maheshwari ma'am, HOD of our college, to welcome Dr. T. Nanda Gopal and Dr. S. Muthukumar. Thank you.
I welcome Dr. T. Nandagopal and Dr. S. Muthukumar from Ramakrishna Mission Vidyalaya of Arts and Science College for the paper presentation section 1. Under your busy schedule, thank you for your acceptance. We hand over the section to you, sir. Thank you, sir. The reason.
Good afternoon, students. I call the presenter for presenting the manuscript ID ICDSSC 13.
Good afternoon, ma'am.
Okay, good afternoon. Sir, you can.
I'm Suchitra. Shall I proceed, ma'am?
Sir, can we continue?
Yes, sir.
Shall we proceed, sir? Muthukumar sir.
Durai, sir.
Sir. Shall we proceed, sir? Sir.
Muthukumar, sir. Shall we proceed, sir? Sujitra ma'am, please wait. I think he has some technical issue. Sir, can you hear me? Muthukumar sir? Delegates, can you?
Hello, sir. Ma'am.
Am I audible, sir?
Hello. Hello.
Sir, can we start the session, sir?
சொல்லுங்க மேடம்.
Shall we start the session, sir?
எஸ் மேடம், you can start now.
Okay, sir. Okay, sir. Sujitra ma'am, you can present. Sujitra ma'am, your voice is echoing. We can't able to hear your voice. Please check it. Sujitra ma'am, your voice is echoing, ma'am. Please check it.
Madam.
Hello, sir.
Shall we start from the serial number? Shall we
Sir, okay,
start
sir.
the order by serial,
Okay, sir.
number, or you have some other?
First one mat 13, sir. Then as to the serial number, sir.
First one?
First one 13, sir. 13, sir.
13.
Yes, sir. Sir, requesting some work, sir. So அதனால உங்களுக்கு first preference கொடுத்தேன்.
Okay, okay. Start பண்ணிடலாங்களா?
Okay, sir. Start பண்ணுங்க. Sir, instruction சொல்லிருங்க, sir.
Instruction
Time
சொல்லிடுறேன்.
சொல்லிருங்க, sir. Okay, sir. Okay. Thank you. Okay. Okay.
I request the participants who are going to present their work. So the participants should complete the presentation maximum of 8 minutes, not more than 8 minutes. The first candidate, Suchitra, to present her work.
I think
Suchitra.
Sujitra ma'am.
Ma'am, can you hear me, ma'am?
Yeah. Now we can hear you.
Okay, ma'am.
Okay. You can present now, ma'am. Already sir told timing, so you can take 5 minutes presentation and we can have a discussion for 2 minutes.
Okay, ma'am.
Thank you.
My screen is not presenting.
Ma'am, you can share your presentation.
Yes, ma'am. Little tower problem. Just a second, ma'am.
Ma'am, have you shared?
Ma'am, just a second, ma'am. It is not getting shared because of the tower problem. Just a second, ma'am.
Okay, ma'am. Can we continue with the next participant so that you
Yes,
can
ma'am.
try?
Yes,
Sir, Nandagopal sir, can we
Start from the first serial number.
can start?
Okay. Okay. So I request the participant Zakir Hussain to present his work. Zakir Hussain.
Good afternoon, sir.
Good afternoon. Good afternoon. Madam, you can present now.
Okay, sir. Okay, sir. Sir, is my screen visible? Visible to you, sir? Sir, can you hear me?
Yes, ma'am.
Okay. Good afternoon to all. Myself, MS Afia Farhana, Assistant Professor of Mathematics and a Research Scholar, PG and Research Department of Mathematics, Jamal Muhammad College, Trichy. I am going to present my paper on topic fuzzy dominator coloring on fuzzy soft graphs. Dr. R. Jahir Hussain, my research advisor, PG and Research Department of Mathematics, Jamal Muhammad College, Trichy. The abstract of my paper is a fuzzy dominator coloring of a fuzzy soft graph GS of t comma v is an appropriate fuzzy soft coloring such that every single vertex of GS of t comma v dominates entire vertex of a color group. In the present work, we initiate fuzzy dominator coloring on fuzzy soft path, fuzzy soft cycle, complete fuzzy soft graph, complete fuzzy soft bipartite graph, and its fuzzy dominator chromatic number is presented, as well as the bounds for fuzzy dominator chromatic number on fuzzy soft graph is established. Introduction of my paper. Rosenfeld described a fuzzy analog of some graph theoretical notion in 1975. The generalizations of Zardis fuzzy set called soft set was proposed by Molesto to solve unclear problems from the viewpoint of parameters. Maggi et al. Started the idea of fuzzy soft set, which is a combination of fuzzy set and soft set, and presented some applications to decision-making problems. Akram and Nawaz originate the notations of fuzzy soft graph, and he gives the applications of fuzzy soft graphs in social network and road network and examine some of their properties. R. Jera talk about the problem of dominator coloring in graphs, and he found bounds and characterizations of several classes of graphs. As Armuham et al. Derived the relation between the chromatic number and the dominator chromatic number, domination number of a graph in 2012. M. Chellali and S. Mapre discussed about the dominator coloring in some classes of graphs. R. Jahir Hussain and K. S. Kanzul determined fuzzy chromatic number of different types of fuzzy graphs in 2014. In 2015, the same authors came out with the idea of fuzzy dominator coloring in fuzzy graphs, and R. Jahir Hussain and Saddam Hussain studied domination in fuzzy soft graphs. And the next section is the preliminary concepts of the graph that I used in this paper. Let V is a non-empty set and R is a parameter set, and T is a subset of R together with a pair of functions alpha E and beta E. Alpha E is a function which with respect to the vertex set, and beta E is the function with respect to the edge set, such that for all x comma y belongs to V and E belongs to T, the relation beta E of x comma y is less than or equal to alpha E of x minimum alpha E of y. Then T alpha, T comma alpha and T comma beta is called a fuzzy soft graph, and this fuzzy soft graphs are denoted by GS of T comma V. The underlying crisp graph of a fuzzy soft graph is equal GS of T comma V is equal to T comma alpha T comma beta is denoted by GS star of T comma V equal to alpha star comma beta star, where alpha star equal to set of all vertex sets such that alpha E of xi is greater than 0 for some E belongs to T, and beta star equal to set of all edge sets such that beta E of x comma V is greater than 0 for some E belongs to T. Fuzzy soft cycle. A fuzzy soft graph is called fuzzy soft cycle if it contains more than one lowest arc. Fuzzy soft path. A path of length n in a fuzzy soft graph is a sequence of distinct vertices x1, x2, x3, etc. xn such that beta t of xi minus 1 comma xi is greater than 0 for every t belongs to T. A fuzzy soft graph is said to be a complete fuzzy soft graph if beta E of x comma y is equal to alpha E of x minimum alpha E of y for every x comma y belongs to alpha star and E belongs to T. A fuzzy soft bipartite graph with fuzzy bipartition V1, V2 is said to be a complete fuzzy soft bipartite if for each node V1, every node of V2 is a strong neighbor. And my contribution, fuzzy dominator coloring on fuzzy soft graph. So directly I go to the definition. Sir, the definition for fuzzy dominator coloring of a fuzzy soft graph is an appropriate fuzzy soft coloring such that every single vertex of GS of T, V dominates entire vertex of a color group. Sir, can you hear me?
Yeah, ma'am.
Yes, madam. Yes.
This is the main definition of this paper. And the fuzzy dominator chromatic number of a fuzzy soft graph is the minimum number of color groups in a fuzzy dominator soft coloring of GS of T, V, and it is denoted by chromatic number FD of GS of T, V, and E belongs to T. Proposition 1, if GS of T, V be a fuzzy soft graph such that GS star of T, V equal to V, E be a soft path of length n greater than or equal to 3, then the fuzzy dominator chromatic number of GS of T, V equal to 1 plus Cn by 3 for n equal to 3, 4, and 5, and 2 plus Cn by 3 for n greater than or equal to 6 for every E belongs to T. Proposition 2, if GS of T, V be a fuzzy soft cycle of length n, then the chromatic fuzzy dominator chromatic number of the fuzzy soft graph is equal to Cn by 3 for n equal to 4 and 2 plus Cn by 3 for n greater than or equal to 5 for every E belongs to T. Proposition 3, if GS of T, V be a complete fuzzy soft graph, then the fuzzy dominator chromatic number is equal to n for every E belongs to T. Proposition 4, if GS of T, V be a complete fuzzy soft bipartite graph, then the fuzzy dominator chromatic number is equal to 2 for every E belongs to T. And the bounds on fuzzy dominator chromatic number of fuzzy soft graph, if we consider a connected fuzzy soft graph of size n greater than or equal to 2, then we need at least 2 different colors to color the fuzzy soft graph, and that becomes a fuzzy dominator coloring since there are 2 nodes which are strong adjacent to each other. So the fuzzy dominator chromatic number lies between 2 and n, and these bounds are sharp for complete fuzzy soft bipartite graph, and the upper bound is sharp for complete fuzzy soft bipartite graph, and the lower bound is sharp for complete fuzzy soft graph. Proposition 1, let GS of T, V be a connected fuzzy soft graph, then the fuzzy dominator chromatic number is equal to 2 for every E belongs to T, if and only if that fuzzy soft graph is nothing but a complete fuzzy soft bipartite graph. Proposition 2, let GS of T,
Ma'am,
V
sorry
be
for the disturbance.
okay. Sir?
Ma'am, can you directly go to your result? What is your proposed result and what is the output? Can you explain directly?
So these are the bounds.
Okay, ma'am.
Proposition 3 is if a node having a strong degree n minus 1, then the fuzzy dominator chromatic number is equal to fuzzy chromatic number. And the proposition 4 is let a GS of T, we are connected fuzzy soft graph, and this is the upper one and lower bound. Fuzzy dominator chromatic number lies between these limits. And in this proposition, the upper bound is sharp for complete fuzzy soft bipartite graph, and the lower bound is sharp for fuzzy soft path. Conclusion, in this paper we define fuzzy dominator coloring for classes of fuzzy soft graphs and its fuzzy dominator chromatic numbers with bounds for study. We further extend the study on some more types of fuzzy soft graphs, and these are my references.
Okay, ma'am. What is your direct contribution on this research work, ma'am, compared to your parent work?
Sir, in my parent work, I found a fuzzy chromatic number for fuzzy soft graph. I extend this to fuzzy dominator chromatic number.
Okay, ma'am. Okay.
Can you give any example for a complete fuzzy soft bipartite graph? Madam, are here?
Yes, sir.
Okay. Can you give any example for complete fuzzy soft bipartite graph?
Complete fuzzy soft.
Or else you can differentiate this complete fuzzy soft bipartite graph and connected fuzzy soft graph. Can you differentiate these
sir.
two? Yes.
Connected fuzzy soft graph means and in that graph, in every pair of vertices, there is a path. Path exists in every pair of vertices. That is connected fuzzy soft graph.
Okay.
Complete fuzzy soft bipartite means if we take every pair of vertices, there is an edge between every pair of vertices.
Okay. Okay, madam. Thank you.
Thank you.
Ma'am, I have a query. Why we need a fuzzy graph?
Why?
Why we need fuzzy? Why you going to fuzzy graphs instead of graphs? Any particular reason is there?
Yes, ma'am. In crisp, we have only vertices and edges, but in fuzzy, we have the membership function, and we define the relationship between two persons in using the membership function. So we have a clear definition about that graph or about that definition. So if we give the membership function, we shall I tell in Tamil, ma'am?
Okay.
So நம்ம மெம்பர்ஷிப் ஃபங்க்ஷன் கொடுத்தோம்னா அந்த ரெண்டு பர்சனுக்கும் இருக்கிற அந்த ரிலேஷன்ஷிப் வேல்யூ வந்து நம்ம தெரிஞ்சுக்கலாம் மேம். Okay, fuzzy graph means the function lies between 0 to 1. So if we give 0.3 to between the two person is 0.3 means it denotes the relation between the two person. If it is 1, then the two persons are very close. So that
0.1 is too close.
Yes.
Okay, ma'am. Thank you.
I request the next participant, Mr. R. Prabhakaran, to present his work.
So can you
You're not clearly audible. Suchitra, you're not clearly audible.
can you?
Okay, madam. Now you can present.
Sir, shall I present, sir?
Okay,
Okay,
madam.
okay, fine.
You just don't give the introduction for this work. You just present your main equations or main work and main theorems and give the final result. Since we have less time, you should complete in
Okay. Okay. Sure, fine.
Okay.
Good afternoon to one of our persons here. I'm Suchitra from Government Arts College, UT. My topic is about grill nano or omega G closed sets in grill nano topological spaces. So this is my abstract. So here I've introduced a new set called grill nano or omega G closed set in grill nano topological spaces. Grill was introduced by Chocket and nano topology was introduced by Lewis Dibaga. And as I'm introduced this grill nano generalized closed set, in the same way I'm going to introduce a new set that is grill nano RMXG closed sets in grill nano topological spaces. So these are the preliminaries. So these are the definitions nano topological spaces. Definition which I'm going to introduce in a minute is nothing but definition is that P, grill be a grill nano topological space. A subset K of A, tau R of X, grill is called a grill nano R omega G closed. If phi of interior of K is contained in H for K contained in H and for all H is nano R open. And for this I've given an example. So here we are taking the universal set as 1, 2, 3, 4 with the relationship 1 and 3 into 4 with the subset P's as 2, 1, 2. And here the topology I've taken is nothing but x, 5, 1 and 1, 2, 4 and 2, 4. And the closure is given by this. And the grill which I've used in this example is nothing but this. So this is my basic definition which I have introduced in this paper. And this is going to topological system. Compare and with the other symbol. Solution given under the and same all grill alpha G closed set is so grill nano RGT closed set. I've given the proof for this and with the case point set. That is example for the theorem. And the next theorem is giving the relationship between grill G alpha closed set with grill nano omega G closed set. And next theorem is nothing but the relationship between nano free closed set with grill nano omega G closed set. So again, two examples and two theorems for the relationship with my set. And this is the diagram which I've got through my analyzation. That is grill nano closed set. All depending my set, that is nothing but grill nano RMG closed set. And in this example, we can see that grill nano MSG closed and grill semi-closed sets are independent from each other. So this is the independent set from my set, and all the other sets are dependent for my set. So I've given the diagram for my work. And next theorem is if E and H are any two grill nano or MSG closed sets in the grill topological spaces, then their union is also a grill nano or MSG closed set. So I put the theorem, I prove this statement with the proof, and I've given an example for this. And the next theorem is if E is a grill nano RMG closed set and if E is contained in H contained in phi of interior of E, then H is also a grill nano RMG closed set. So I proved this theorem with the result. And the next theorem is if E is a grill nano RMG closed in the grill nano topological space, then phi of interior of E minus E does not contain any non-empty nano regular closed set. Yeah, I proved this theorem. And the next definition is nothing but grill nano RMG open set. So this is the definition for grill nano RMG open set. That is, if the complement is grill nano RMG closed, then the set is called as grill nano RMG open. So for this, I've proved a theorem that is, if interior of phi of K is contained in S, which is contained in K, where K is grill nano omega G open in the grill nano topological space, then S is a grill nano omega G open sets. So I've given the proof for this theorem. So this is the proof for this theorem. So this is my work. And these are all my references. So any queries?
Ma'am, what is the difference between the nano set and the grill nano set?
Sir, if you take the topologies of nano itself is a very small particle. So when you come,
ma'am, first, excuse ma'am, just
sir, yes, sir.
How can you define a set, ma'am? First, then we can go to nano.
Sir.
So the participants can compare both the sets.
So can you please repeat, sir?
Sir, ma'am, just what is the relation between the set and the nano set?
Set and the nano set, sir.
Yes, ma'am.
So topological set, that is so when you nano topological is a small particle, sir. If you take the topologies of nano topological space, so in ordinary topology we'll be having 29 topologies for a 3-element set. That is, if you come for a nano topological space, the whole topological space will be getting shrink. That is, if for my set I'm getting in topological space we can get 29 topologies. When you come to the nano topological space, your topological space will be getting shrink. For my space, I'm getting only 4 topological space in a grill nano topological space. So when you that is the difference. When you compare, when you combine more and more sections like topology and grill topology and grill nano topology, when you combine these things, your topologies, topological spaces will be getting shrinked, and you will be having a different topological space. So that is the thing here.
Okay, ma'am. Thank you.
Any more questions, sir?
Any other questions from the participants? So if there is no question, you can leave now.
Thank you, sir. Thank you.
Next, I call Mr. R. Prabhakaran to present his work. Prabhakaran.
Mr. R. Prabhakaran?
Okay. We can move to the next participant. So I request Arun Kumar D to present his work.
Okay, sir.
Prashant
Good
is
afternoon.
asking, don't take more time.
Okay, now, okay.
Okay.
Okay, thank you. Sir, is it my screen is visible, sir?
Your screen is visible. You can present now.
Okay. Yeah, okay, thank you. So good afternoon to all. I am Arun Kumar, and my topic is integral boundary value problem for nth order impulsive integral differential equations. So in this paper, we study the existence of positive solution for the system of nth order impulsive integral differential equation with integral boundary conditions by using Leray-Skadar fixed point theorem. And impulsive differential equation. So impulsive differential equation means in many evaluation process, there are some sudden changes. At that time, differential equation arises in the form of impulses. So such as shocks, harvesting, and natural disaster like that. And the integral differential equation is an mathematical expression which includes both integrals and derivatives. And in this paper, we consider the nth order impulsive integral differential equation with integral boundary condition, which is defined in equation number 1. And in this first equation, the functions f, h are continuous, and the impulsive function also. Here, impulsive function is an discontinuous. That means piecewise continuous function. So, and the g is non-negative, and v is continuous, and thus it does not vanish. And next we define a piecewise continuous function. So here PC n minus 1 means it is a piecewise continuous function. Next, so this is an Leray-Skadar fixed point theorem. To prove the existence result, first we need to prove it is a completely continuous operator and the set X is bounded. Next, we will move to the next lemma. So in this lemma, we prove the solution of the equation 1, that is x of t, which is given in equation 4, and in this equation 4, h, g1 and g2 are defined in equation 5, 6 and 7. So for that, we take a given equation xn minus 1 of xn of t, and if we integrate that term, and by using boundary conditions means we get equation number 9. Similarly, if we integrate n minus 2 times, we get the equation number 10. And let t is equal to 1, we get a equation number 11, that is x n minus 1 of 0, and substitute the x n minus 1 of 0 in equation 10 means we get the equation number 12. After that, we use the another boundary condition and get a result, that is we get in 4, and h, g1, g2 are defined in the equations 5, 6 and 7. So this is the sufficient part, and converse part can be proved by differentiate the given this equation 4, equation number 4 by n minus 1 times, we get the result x n of t is equal to minus w of t. So this is the equation 4 is the solution of the problem. And next, so in this remark, we prove the nth order differential equation, it is very complicated. So we can convert that into second order impulsive integral differential equation, and we proved the existent result for this one, equation number 15. And next, existence result. So in theorem 2.1, the nth order boundary value problem 1 has a solution if and only if the second order nonlinear impulsive integral differential equation 15 has a solution. So by taking y of t equal to x n minus 1 of t, we proved that we proved that if second order impulsive integral differential equation has a solution if and only if nth order boundary value problem also has a solution. So this is a proof of that theorem. And in this theorem 2.2, we proved the solution for y of t, that is that for second order impulsive integral differential equation. So this proof is similar to the lemma which we'll discuss in lemma 1.2. So next, to prove a completely continuous operator, we define an operator a in the by the equation a y of t. So here a y of t and a y dash of t greater than or equal to 0, and a y dash of 0 becomes 0. And next, in theorem 2.4, we proved that the operator a is completely continuous. So to prove the completely continuous, we need to first prove uniformly bounded and equicontinuous. So by using Asla-Ascalay theorem, we proved that the operator a is completely continuous. So here we proved that result. So first, we by the hypothesis a1 to a4 that a is continuous. So we need to prove this a is uniformly bounded. So for that, we define a closed ball BD, and the modulus of ay of t less than or equal to supreme of the function. Therefore, it is functions is less than or equal to some constant means, that is supremum value means it is uniformly bounded. Then we need to prove the uniform equicontinuous. So for that, we take t and t dash that is belongs to 0, 1, and we proved that this tends to 0. Therefore, the family is a family of equicontinuous functions. Then by the Asla-Ascalay theorem, the operator a is completely continuous. So next, by assuming the hypothesis a1 to a5, we need to prove the boundary value problem 1 has at least one positive solution. So for that, we denote n of a, and we need to prove this n of a is bounded. By taking norm, we prove that less than or equal to some function. So therefore, this n of a is bounded. So here the operator a is completely continuous and this is bounded. Therefore, by Leray-Skadar fixed point theorem, this x of t is a positive solution of the higher order boundary value problem equation 1. So I consider this is an example for the problem, and in this example I proved this uniformly bounded and equicontinuous and completely continuous. Then by the theorem 2.5, the problem 18 has at least one positive solution. And these are my references. Thank you. Any questions now?
Anand,
Yes, yes, sir.
What is the use of using fixed point, that is SCADA fixed point and Laris fixed point theorem? What is the difference? Is there any convenient to use this particular fixed point theorem?
So there is no difference between them. Now here I use the Lares-Carter fixed point theorem. We can prove this for another fixed point theorem like Banach fixed point theorem, Schaffer fixed point theorem. Here I use the Lares-Carter fixed point theorem.
Is it possible to use some other fixed point theorem to find the solution, find existence of solution?
Yes, sir. Yes, sir. Is it possible to use some other fixed point theorem?
Okay, okay. So in your
but in this
yes,
but in this theorem we need to we use the Lares-Carter fixed point theorem. In this Lares-Carter fixed point theorem we need to prove the operator is completely continuous and the n of a is bounded. That's why we are taking that Lares-Carter fixed point theorem and proved that one now.
Okay, okay. So in your presentation you have one remark.
Yes, sir.
So in that remark you have said that it is complicated to solve the nth order differential equation.
Yes.
So you have converted this nth order to second order differential equation.
Yes.
Okay. How can you explain how you have converted this nth order to second order?
Actually, just a minute. Yes. So here we taking this as an second order equation. So in first nth order equation we taking the like impulsive condition for n for the degree n, and here we taking for first degree, and the boundary condition also we taking for nth order. We convert that into second order here. Here y double dash of t equal to v of t plus function gets changed. Here we taking the integral differential equation. So and this is the impulsive condition for second order.
Mandolana asked me about how do you convert nth order to second order differential. Now you are showing that this is a second order integral differential equation.
Yes.
But where is your nth order integral differential equation?
This is the yes, now. So this is the nth order differential equation.
Yeah.
Here we taking
this, how can you convert this into second order? That is
yes. Here the function is continuous. F is a we are taking that function f is a continuous function. So in that second order equation also we are assuming some function f is a continuous function.
Okay, thank you. Any other questions from participants?
So if there is no questions, Arun Kumar, you can leave.
Okay. Thank you so much. Thank you.
Okay.
Thank you so much.
I call Prabhakaran or Prabhakaran, serial number 2, to present. If Prabhakaran is not there, I request Bharati, yes, and Devi T to present. Yes, Bharati. Bharati. Yes, Bharati. So if Bharati and Devi is not there, I call yes, Divya to present her work. Divya.
Yes, sir.
Are you there?
Yes.
Are you ready? Are you ready to present?
Yes, sir.
Okay, you can present now.
Okay, sir. Good afternoon to all. Myself Divya. Now, my topic is thermally radiative flow of a gas nanofluid with magnetic field and heat generation or absorption over a stretching plate. Abstract heat absorption or magneto-convective flow of a gas or nanofluid over a stretching plate. The governing models are converted into a nonlinear ODE model, and they are solved analytically using homotopy analysis method. The various of physical parameters are examined with fixed values. It is found that the fluid temperature is an enlarging function of the fluid parameter. Designed as a zero redshift. Nanofluid is a fluid containing nanometer size particles called nanoparticles. Thermal radiation by which energy in the form of small and magnetic field is a vector. A magnetic field is a vector field that describes magnetic influence on moving electric charges, electric currents, and magnetic materials. Equation. Second momentum equation. Third one is temperature equation. Fourth one is volume fraction. Sir?
Ma'am, continue. Divya ma'am, you can continue.
So which slides are now it is presenting?
Main slide ma'am. Your heading. Research heading.
So it is moving or not, sir?
Ma'am, you are in first slide only. Okay. Okay, carry on.
Come to the main equation.
Mathematical formulation. First equation is
Ma'am, it's
represented as continuity equation. Second one is energy equation. Third one is temperature. Fourth equation is volume fraction. Here you represent as velocity in x direction, v in y direction, beta is represented as Chasm fluid parameter, sigma is electrical conductivity, alpha T is represented as thermal diffusivity, rho is represented as density, dB is represented as Brownian diffusivity, and dt is represented as thermophoretic diffusion. These are my boundary conditions. The similarity transformations are introduced as below. Using the similar boundary conditions and similarity transformation, I have solved these equations. That is nonlinear PD is converted into as ODE.
By using Ham solution, I have solved these ODE equations and I have obtained the results. By using symbolic calculations by Mathematica, I have solved these calculations. These are my H curve value. Here, the H curve, we can choose values anywhere in the straight line, but I have chosen in the middle, so I have chosen this. These are my H curves. This is velocity of H curve. This is temperature of H curve. This one is volume fraction of H curve. Next one, the Prandtl number. Prandtl number, when temperature decreases, Prandtl number will increase automatically. Here, heat generation, temperature increases when heat generation is also increases. Temperature decreases when radiation increases in this graph. Here I conclude that the heat absorption on magnetoconvection flow of a Kazan nanofluid over a stretching plate. The governing equations are formulated and transformed into an ordinary differential equations by using similarity transformations. The resulting equations are solved using Ham method, homotopy analysis method. The temperature theta decreases with increasing value of Prandtl and increases with increasing value of magnetic field. The nanoparticles pi decreases with increasing value of number and increases with increasing value of Kazan fluid parameter. These are my references. Thank you, sir.
So you have chosen Kazan fluids, right?
Yes, sir. Yes, sir.
Is there any particular reason to choose Kazan fluid? Advantage of choosing Kazan fluid?
So it is very easy to solve, so that I have chosen Kazan fluids, sir.
So for plotting the graph, what kind of softwares you have used?
Mathematica software I have used, sir.
Okay. Any questions from the participants? Any questions from the participants? So if there is no questions, we can move to the next participant. Okay, thank you.
Thank you, sir.
So I request next participant Damayanti to present her work. Dr. G. Damayanti.
So Devi is here. Shall I present now? Sir, Devi is. Shall I present, sir?
Okay, okay, madam.
Okay, one sir. Okay. So one second, sir.
Okay, ma'am. You can
Sir, one second.
start a speaker. Okay, ma'am.
One second. Sir, visible, sir?
No, ma'am. Your PPT is not visible.
Sorry, sir, once again, technical issue, sir.
Okay, ma'am. Can we continue after one
Okay, sir.
presentation? Can we call
Okay, sir.
someone? Okay, ma'am.
Okay, sir.
Okay. You can leave. You can.
Okay, sir.
Ma'am, Tamil ma'am. Dr. G. Tamil Kanagambika. Kanagambika, ma'am.
Sir, good evening, sir.
Ma'am.
Shall I proceed, sir?
Kanagambika, ma'am. Okay, ma'am.
Okay, sir. Thank you, sir.
Okay.
Sir, is my screen is visible now?
Okay, ma'am. It's visible.
Okay, thank you, sir. Good afternoon to all honorable present here. I am K. Kanagambika from Bellalur College for Women. I am going to share some few views about odd-even concurrence labeling of graphs. This is my abstract. We have introduced a new labeling called
Ma'am, your PPT is not visible. You are not sharing the screen, I think.
Sir, I have shared, sir.
But your PPT is not visible, ma'am.
Sir, just a minute, I will check it out, sir.
Okay, okay, ma'am. Okay.
Sir, is my screen is visible now?
Okay, ma'am. Okay, okay. You can continue.
Shall I continue, sir?
Okay, ma'am. Okay.
Thank you, sir. Sir, this is my abstract. Here we have introduced a new labeling called odd-even concurrence labeling, and we have invested for few graphs such as bipartite graph, cone graph, splitting graph of a star graph, and we extended it for a cycle graph. Then tensor product of two graphs and shadow graphs. These are my introduction. Graph labeling plays a vital role in various fields. In many fields, motivated by this, many researchers are now introducing new concepts in graph labeling. In the modern era, all the informations are digitalized and shared through internet based on networks and virtual networks and communities. In privatization, everything is open to all. By using cryptography, the data can be privatized by coding and decoding, which is the growing topic now. Now, we like to combine graph theory and cryptography. The cryptography is mostly based on concurrence labeling. So we like to introduce the concurrence in labeling, and we have introduced a new definition, odd-even concurrence labeling. In this, we have labeled all the vertices with odd number and edges with even number. The vertices and edges must be satisfied the condition f of vi concurrent to f of bj mod ej, where vi and bj are nothing but the edge vertices incident with the edge e. These are some of the preliminaries we have considered, and this is the odd-even concurrence graph. Now, while labeling the vertices and edges, we have the constraint that the vertices are limited only up to 2k plus 1, and the edges are limited up to, the label for the edges are limited up to 2k. The k is nothing but the minimum number of twice the cardinality of vertices and twice the cardinality of edges. The first we have considered in complete bipartite graph. K m comma n be a complete bipartite graph with the vertices m comma m plus n, and the number of edges in this graph is mn. Here k is equal to minimum number of twice m plus n, twice the product of mn. We have considered twice m plus n as the minimum one, and the vertices in the bipartite set U is named as U1, U2, etc. Um, and the vertices in the bipartite set V is named as V1, V2, etc. Vn, and the edges are named as E1, E2, etc. Emn. Then the edge E1 is initialized as, which is connecting U1 and V1. The edge E2 is a edge connecting U2 and V1. Similarly, the edge EM is connecting the vertices UM and V1, etc. EMN is an edge connecting UM and VN. We have defined the labeling as the vertices are labeled with the integers 1, 3, etc. up to 4m plus 4n plus 1, since we are using only odd numbers, and the edges are labeled with the even numbers 2, 4, etc. 4m plus 4n. And the vertices are labeled with the definition 2i minus 1, where I is equal to 1 to m, and the corresponding vertices in the bipartite next set is labeled with 2m into n plus 1 minus 2mj plus 1, where j varies from 1 to n, and edges are labeled with the definition 2mn minus 2 into I minus 1 for all L varies from 1 to mn. To prove the existence of congruence labeling, we have checked the condition f of ui minus f of vj is congruent to mod ej. We have done the calculations and proved that 2mn minus 2l plus 2 divides the difference of the vertices. The example is given here. We have considered a complete bipartite graph. The vertices are labeled with red color and edges are labeled with black color. Then the difference of 13 minus 1 is divided by 12. 13 minus 5 will be divided by 8. Therefore, the congruence exists in the bipartite graph. Likewise, we have considered for another graph K4, 4. This is proved in a cone graph. Cone graph is nothing but in a path Pn, which is incident with every vertices in the path Pn is incident with a K1. Like this, we have constructed the cone graph, and we have given the definition for labeling the vertices and edges in the cone graph. The example is given here. This also satisfies the condition. The difference of the vertices will be divided by the label which is used to label the edges, corresponding edges. Similarly, we have considered few graphs like splitting graph. Splitting graph is nothing but in a star graph, we introduced a vertex V and it is connected to the neighborhood of that U, which was given in the preliminaries. The definition of the graph is given in the preliminary. Here, the vertex set is U1, V, U1, V2, etc. Vn, and U, U1, U2, etc. Un. Then the vertices V, V1, V2, etc. Vn are the vertices of the star graph, and V is the new apex vertex, and the introduced vertices are U, U1, U2, etc. Un, which are added to form a given graph, the splitting graph G. For E1, E2, etc. E3n are the edges, for E1, E2, etc. En are the edges of Sn, the given graph star graph, and En plus 1, etc. E up to E2n are the edges which are added to U and Bi's, and the E2n plus 1 to E3n are the edges which is adjacent to Bn Ui. Here our K is equal to 4n plus 4. The vertices are labeled by Va is labeled, f of Va is labeled by 6n minus 4i plus 7, where I varies from 1 to n, and the apex vertex f of V equal to 1 and f of U equal to 3. F of Ua is equal to 2i plus 3, where I varies from 1 to n. Our edges are labeled with the given thing 7n minus 4j plus 2 for j varies from 1 to n. For j varies from n plus 1 to 2n, it is labeled with 10n minus 4j plus 4. Then for 2n plus 1 to 3n, it is labeled with 2j minus 4n plus 2. These constructions also satisfies the definition of concurrence labeling, which is also satisfied by considering an example for n equal to 8, which can be done for any number of n. Likewise, we have proved it for a graph which is obtained by joining two copies of cycle Cm of even order by a path Pn and is which exist odd even congruence graph. The example is given here. Likewise, we have proved it for tensor product of two graph K1, n and P2. The definition was given, which is used to label the vertices and edges. The graph is given here. Here we have considered n equal to 4 and the path is P2. The next one is shadow graph. In this graph, we are having two copies of Pn and we have joined the edges with the adjacent vertices. Here also we have defined the definition f of ui to label the vertices, and for edges we have used the modulus of f of u minus f of v, where u and v are adjacent to each other. This is the example for the shadow graph D2 P6. D2 denotes we are having two copies of path P6. It can be extended for Dn also. the graph labeling in graph theory have paid more attention for many researchers. Here we have achieved it for few graphs. This can be extended to for some other family of graphs also in future. These are our references.
Okay, ma'am. Thank you, ma'am. You are restricted your research for edges to 2K plus 1. What happen if we take either K or 2K?
Sir, we have to label only with the odd number of vertices, sir. K denotes the ordinality of, since we need odd number, so I have multiplied by 2, sir.
Okay. And what is the practical application on your research finding, direct bearing of?
Sir, it can be applied in networks, sir, in electric network, in anywhere, or for placing the loads. We can calculate the distance by the label of edges. We are having like many practical examples, sir.
Thank you. You are plotting this graph using latex disk,
yes,
or
sir.
Okay.
Yes, sir, we have typed in latex.
Is there okay? Is there any question from participants? Is there any question from participants? Okay, ma'am. Thank you, Kanamika, ma'am. Thank you for your presentation.
Thank you, sir.
Okay. Now we call.
Thank you very much for giving the opportunity, sir.
Thank you. Now we call the Devi T to present his research findings.
Yes, sir.
Devi T.
Yes, sir. Yes, sir.
Okay,
Yes. Oh, one
you
second.
can continue.
Okay, sir. One second, sir. Sir, my PPT is this.
No, ma'am. Your PPT is not visible.
Sir, actually, share button is not enabled for me, sir.
Okay, ma'am. Try to connect in some other device.
Okay, sir. Okay, sir. Then after 2 members, I will just send, sir.
Okay, ma'am. You can try some other device. I will call next participants to present because we are running out of time.
Okay. Thank you, sir. Thank you, sir.
Okay, ma'am. Okay. Kausalya, P. Kausalya, ma'am. Can you present now? Are you ready? P. Kausalya.
Sir, good afternoon, sir.
Ma'am. Okay, you can present now. You can
Yes,
present
sir.
your research.
Okay, sir. Just a minute, sir.
Okay. Upcoming research participants are requested to get ready for present your research work so that we can finish the session as quick as possible. Okay. A kind request. Upcoming researchers, those who are going to present your research work, get ready for your presentation. Kausalya, ma'am, you can present now.
Just a minute, sir.
Okay.
Sir, is it visible, sir?
Okay, ma'am. Your PPT is not visible.
Sir, is it visible, sir?
Okay, ma'am, you can present your research work.
Oh, thank you, sir. Thank you, sir.
Okay.
And myself, Mrs. Kausalya, PhD part-time research scholar of Thiru Kolanjiyappan Government Arts College from Virudachalam. First of all, I thank the organizer team of Gobiarts and Science College to propose my research work in this webinar. And by guidance of Dr. V. Ganeshan sir and Dr. Satyaseelan sir, I have proposed this work. Strong anti-fuzzy graph and its self-complement. My abstract of this paper is actually we have present the representation for edge value in the anti-fuzzy graph and strong anti-fuzzy graph. For that we have take the of fuzzy graph, and moreover we derive the four properties for obtaining the self-complementary graph from the anti-fuzzy graph. For that we have provided the examples, and moreover we extend our result to prove for a strong anti-fuzzy graph to be a self-complementary, and also a complement anti-fuzzy graph does not preserve the self-complement. These are all the work of my guide. Actually, fuzzy set theory is a generalization of crisp set where the elements of set are having various degree of membership. It was introduced by Lotfi A. Zadig in 1965. Fuzzy graph theory, it has a numerous application in decision-making problem. It was originated in 1975 by Rosenfeld. Anti-fuzzy graph, it is a new recent development area and is an extension of fuzzy graph. It was studied by Akram in 2012, and recently it was the basic definitions are introduced by R. Mutturaj and A. Sasireka in 2019.
Ma'am, your PPT is not moving. Your slides are hanging, or you are not.
Sir, now, sir?
Ma'am, it's
still it is in the first page. Still it is in the
Sir,
first page.
Is it so the definition, sir?
No, madam, still it is in the first page. Still
Okay,
it is in the first page.
Okay, so let me check, sir.
Okay.
Now is it moving, sir?
No, ma'am. Your presentation is left, I think. You are not presenting your screen.
Yes, sir. Let me check, sir. Sir,
Yes, ma'am, visible?
so is it moving, sir?
Yes, ma'am. Okay. Can you use
Okay, sir.
full screen? That is F5 or from beginning?
Okay, sure, sir. Sure, sir.
Okay.
This is the introductory part, and these are all the basic definitions which are used to propose my research work towards anti-fuzzy graph. Fuzzy graph represents G of sigma comma mu, where sigma represents the vertex and mu represents the edge set. Actually, we are all known that a graph is an ordered pair of vertices and edges. The vertices are represented by V and edges are represented by E. The edges is nothing but the relationship between the vertices. And why we are using fuzzy graph means in a crisp set we cannot get an accurate value. In a fuzzy graph, we can solve the decision making problem in real life. That is the fuzzy graph consisting the values between 0 and 1. That is fuzzy graph which accepts all the members, all the elements as a member. But in a crisp set, all the elements are not accepted in a crisp set, because the crisp set having a value is only 1, 0 and 1 only. So if it is a member, then we can assign the value of the set is 1, or if it is not a member, then we can assign a value is 0. But in a fuzzy graph, it is not like a crisp set. So that we are using fuzzy graph. And anti-fuzzy graph is a new representation. It's a new development of fuzzy graph. The same anti-fuzzy graph is like a fuzzy graph. It has also a vertex set and edge set, but the relationship between the edges is more than the maximum value of those two vertices. Definitions, and here in my paper we have present the clear representation for representing the edge value of anti-fuzzy graph. For that, we are plot a diagram which shows the anti-fuzzy graph, and sigma of x, sigma of y, sigma z are denotes the vertex, and mu of x comma y is nothing but the relationship between a and b, which is denoted by mu of x comma y. This value is taken by the maximum value of a and b. And this is also the framework to obtain the membership value for a strong anti-fuzzy graph. Strong anti-fuzzy graph means the anti-fuzzy graph is also a fuzzy graph which have the vertices, but the edge value is which is equal to the maximum of a comma b. That is what strong anti-fuzzy graph. And we propose this theorem: if G is a strong anti-fuzzy graph, even only if its complement is also a strong anti-fuzzy graph. And for that, we are giving a diagram. The first figure shows the strong anti-fuzzy graph, because this figure consists of 4 vertices, which are 0.5, 0.9, 0.3, 0.7. And we just only present the 3 vertices, 3 edges, 0.9, 0.9, 0.7. Strong means the relationship between 0.5 and 0.9 is indicated by 0.9. That is the maximum value of the 2 vertices is 0.9. So that is what represented by an edge. So this is what is strong fuzzy anti-fuzzy.
Kaushalya ma'am, your PPT is not moving.
Sir, is it now moving, sir?
In the introduction.
Okay, sir. Let me check, sir. Sir, let me check, sir. Yeah, sir.
Just give
Yeah, sir. I
F5.
have already put F5, sir. But in my screen, it is in full screen. But why? I don't know. It is not visible there.
Okay.
Sir, is my screen source a diagram, sir?
Yes, ma'am.
Yeah. So this is the example of self-complementary graph of strong anti-fuzzy graph. Figure 6 shows the strong anti-fuzzy graph. It has 4 vertices with 3 edges. From this, we have found a complement of its graph. So what I proposed, what we have proposed to the work is, if suppose we take a strong anti-fuzzy graph, then we get a complement. Then if suppose we derive a complement from this graph, then the both graphs are same. That is G equal to G complement. From here, what we have say is the complement of anti-fuzzy graph and the strong anti-fuzzy graph are same. So that is what the self-complementary. These cases are all existing when the 4 vertices are suppose having a equal number of membership value, or the 4 vertices with 3 membership values equal, or one is different, then only we can arise a self-complementary fuzzy graph. Otherwise, we cannot found a self-complementary fuzzy graph. And this is the example of self-complementary fuzzy graph, which cannot exist in a complete anti-fuzzy graph. Complete anti-fuzzy graph means the vertex is adjacent to each other vertex, and moreover, the membership value of an edge will represent by the maximum of those vertex value. So that is what complete. If you suppose we have found a complement of graph, then what we get is, let us take 0.8, 0.6. It have a membership value 0.8. So if we suppose find a complement means we have no edge. So the same way, if suppose take a complete anti-fuzzy graph, then we definitely got an isolated vertex of complement graph. So what we have concluded is the complete anti-fuzzy graph does not preserve the self-complementary. And this is my conclusion of this paper. Actually, we have worked out this property. We have concluded that is n of mu of x comma y plus n of mu bar of x comma y equal to a into a minus 1 by 2. That means the number of edges in a strong anti-fuzzy graph plus number of edges in a complement of strong anti-fuzzy graph, which satisfies the equality a into a minus 1 by 2. That is, a represents the number of nodes in the graph. Conclusion. And these are all my references to take out to propose my research work, sir. Sir, is there any queries, sir?
Madam, in your work you have used fuzzy graph and anti-fuzzy graph.
Yes, sir.
Is it right? Can you
Yes, sir.
differentiate, if you differentiate these two the researchers will be clear on a fuzzy graph and anti-fuzzy graph.
Sir, I'm not understanding, sir, what you have asked,
If
sir.
you differentiate what you mean by fuzzy graph and what you mean by anti-fuzzy graph,
Yes, sir. Yes, sir.
by giving an example, the researchers can easily understand.
Yes, sir. Yes, sir.
Yeah.
Actually, graph would consist of vertices and edges. The same way, fuzzy graph is represented by only by the membership value assigning. The same way, the procedure are always same in anti-fuzzy graph. That is, the representation of vertex value are all same in fuzzy graph as well as the anti-fuzzy graph. The edge value only is the representing of edge value is only varies from fuzzy graph and anti-fuzzy graph. In a fuzzy graph, we take the edge value by considering a less than or equal to the corresponding vertices. But in an anti-fuzzy graph, we represent the edge value by considering the maximum of those corresponding vertices. That is what the difference between both graphs are.
Okay, ma'am. Is there any question from participants, audience?
So if there is no question.
Excuse me, sir. Excuse me, sir.
Okay,
Sir?
okay.
Sir, I have one question.
Okay, okay, ma'am. Okay.
Sir, okay. Kausalya, ma'am, what is the advantage of using anti-fuzzy graph, ma'am?
Actually,
Instead of
in
using
this
fuzzy
paper,
graph?
yeah, ma'am, it is a recent development area. Now we are only formulating the basic concepts only, and hereafter we using the applications of anti-fuzzy graph in network and image clustering problem, ma'am.
Okay, ma'am. Okay. Thank you, ma'am. Thank you. Thank you, sir.
Okay, thank you. First, M. Sangeeta to present this work.
Thank you, sir.
Okay, ma'am.
Good evening, sir.
Good evening.
Good evening, sir. Thank you for given me this opportunity, sir. And myself, M. Sangeeta Vani. It is mistakenly given as Sangeeta in that brochure, sir. Please, I request you to change it, sir. Myself, M. Sangeeta Vani, second MSc Mathematics from Dr. NGP Arts and Science College, and my research article title is Numerical Analysis of a Darcy-Fritschmer Flow of a Chemically Reacting Williamson Fluid over a Stretching Sheet. And in my paper,
Just to present your, excuse me, you just to present your work. You are not
okay,
presenting
sir.
now.
So now, sir, is now my screen is visible, sir.
Visible. You can present now.
Okay, myself, I am Sangeeta Vani from second MSc Mathematics, Dr. NGP Arts and Science College. My research article title is Numerical Analysis of a Darcy-Fritschmer Flow of a Chemically Reacting Williamson Fluid over a Stretching Sheet. And in my paper, we examine the flow of a Williamson fluid in presence of Darcy-Fritschmer porous medium over a stretchy plate with Cantonio-Christoph dual flex. And this problem was solved by use of MATLAB with BVP4C solver, and the impact of the governing parameters are analyzed graphically and use of tables. In recent years, non-Newtonian fluids non-Newtonian fluids obtained the attention of various researchers due to its various application in enormous fields. And for this non-Newtonian fluids, there are various of models are developed to characterize the behavior of the non-Newtonian fluid. One of those models is Williamson fluid model, which was developed to describe the properties of viscoelastic shear thinning fluid. And the porous medium is a solid body containing void spaces and pores which are distributed randomly. And the next one I here used is the Darcy's Rechmer forest medium. The Darcy law was proposed by Henry Darcy, which describes the relation between flow rate and pressure gradient is linear. When there exists a nonlinear relationship, the Darcy's law will become inadequate in those situations. For those situations, Rechmer introduced an additional term, the Darcy law. Problem. Here the first equation is the equation of continuity, second equation is for equation of momentum, third equation is for temperature, and fourth one is for concentration. Here u and v are the velocity in x and y coordinates, nu is the kinematic viscosity, k2 is the ferocity parameter, cb is the drag coefficient, t is the temperature, and alpha is the thermal diffusivity, T infinity is the free stream temperature, rho is the density, Cp is the specific heat capacitance, and dB is the mass diffusivity, C is the concentration, C infinity is the free stream concentration, and omega T and omega C are relaxation time for heat and mass flux respectively. And the boundary condition here expressed or what I used. And I use these parameters eta, u, v, theta and pi to transform the PDE equations into the following ODE equations. Here F is the velocity and W is the Williamson parameter, HA is the Hartmann number, lambda is the ferocity parameter, FR is the Fritschmer number, and PR is Prandtl number, R is the radiation parameter, HG is the heat generation parameter, gamma 1 is the relaxation time for heat flux, SC is the Smith number, CR is the chemical reaction parameter, gamma 2 is the relaxation time for mass flux, and the corresponding boundary conditions are f of 0 equal to Fw, which is known as suction or injection parameter, and f dash of 0 equal to 1, theta dash of 0 equal to 1, phi of 0 equal to 1, and f dash of infinity equal to 0, theta of infinity equal to 0, and phi of infinity is equal to 0. And this is the table we obtained for the various values of Williamson parameter, ferocity parameter, Fritschmer number, and suction
Excuse
parameter.
me.
Yes,
You present your graph.
Okay, sir. And this is the graph we obtained for various values of velocity for various values of lambda and WE, which is for ferocity parameter and Williamson parameter. While we increasing the values of ferocity parameter, the velocity will decrease, and for the same, while we increasing the values of Williamson parameter, the velocity will also decreases. And this is the graph for temperature for various values of relaxation parameter and radiation parameter. While we increasing the relaxation parameter values, the temperature will decrease, and while we increasing the values of radiation parameter, the temperature will increase. And this is for the graph for concentration for various values of relaxation parameter for mass flux and chemical reaction parameter. While we increasing the values of relaxation parameter, the concentration will decrease, and for the increasing the values of chemical reaction parameter, the concentration will decrease. And as I here concluded that the effect of double heat flux and MHT flow of Williamson fluid with Darcy-Fritschmer forest medium is analyzed here. The solutions are obtained by use of BVP4C solver in MATLAB. And my findings are that thickness of momentum boundary layer is decreasing when increases the values of ferocity parameter, Williamson parameter, and Fritschmer number. The heat generation case enhances the thermal boundary layer thickness. While increasing the values of radiation parameter, the temperature increases. The thickness of the solute boundary layer is high in generative chemical reaction than the destructive chemical reaction case. And these are my references. Thank you.
Any questions from the audience? Any questions from the audience? So if there is no question, I request Magadishwar yes to present his work.
Thank you, sir. Thank you for the
Yes. Oh, thank you. Yes, Magadiswaran to present his work.
Is it visible my screen? Sir?
Your screen.
Oh, a warm good afternoon, honorable person here. I am Magadiswaran, PhD research scholar, Department of Mathematics, Sri Ramakrishna Mission Vidyalaya, College of Arts and Science, Coimbatore. Then,
Mr. Magadiswaran, your PPT is not visible. Sangeeta ma'am? Yeah. Just mute your audio. Sangeeta Vani. Sangeeta Vani ma'am, mute your audio. Yes, you can proceed. Mr. Magadis.
Okay. First, I delight to thank organizing committee and the chairpersons of this conference because of providing me an opportunity to participate in this conference. Thank you all. Now to present my work. The title of presentation is Fear Effect on Delayed Interpretation Model with Ratio-Dependent Functional Response. These are my plan of presentation. First, abstract. In this work, we consider to investigate the interpretation model with fear effect and the time delay, to analyze the existence of possible equilibrium points, then local stability and hope analysis of non-delayed and a delayed model by varying the fear parameter and the delayed parameter respectively. Finally, numerical simulations are carried out. Next, model for formation. The three species food chain model with the holding type 2 functional response is given in equation 1. And we incorporate fear into our border 1, and the fear term is 1 divided by 1 plus f1 into b. Here f1 is the level of fear, and assuming the following conditions, we get the modified model which is given in equation 2 with the suitable initial conditions. Next, existence of equilibria. E1 be the predator free equilibrium point, E2 is equilibrium point, and E star is the interior equilibrium point. Next, in order to determine the stability of the system 2, for that purpose, we calculate the Jacobian matrix and is given in equation 4, where A is given below. For Ij is equal to 1, 2, and 3. E1 is unstable, E2 is locally asymptotically stable if this condition is held. E star is locally asymptotically stable if the Roos criterion condition are satisfied. Proof of theorem. The Jacobian matrix at E1 is J of E1 is given in equation 5. The eigenvalue of above Jacobian matrix is J lambda 1, lambda 2, and lambda 3. Here lambda 1 is greater than 0, so E1 is unstable. J of E2 is the Jacobian matrix at E2 is given in equation 6. The eigenvalues of J of E2 are lambda 1, lambda 2, and lambda 3. Asymptotically stable if this condition is held. Then Jacobian matrix at interior equilibrium point is given in equation 7, where Sij values are given below. Ij for Ij is equal to 1, 2, and 3. The characteristic equation of above Jacobian matrix is given in equation 8, and epsilon 3 values are given below. If here Roth-Lewis condition are satisfied, then we say that E star is locally asymptotically stable. Next, the Hope fabrication analysis. To analyze the fabrication of the system analytically according to the effect of fear. Theorem 2. If the system satisfies the following condition, then the system has enters into Hope fabrication. Then for proof of this theorem, characteristic equation 8 can be expressed and given in equation 9. And then general characteristic roots are given below. Substituting rho 1 is equal to r plus is in equation 9, we get a plus ib is equal to 0. The value of a and b at f is given in given here. Then differentiating A and B with respect to F, we get equation 10 and 11. Multiplying 10 and 11 by psi 1 and psi 2 respectively, and add these two equations, we get equation 12. Substituting R is equal to 0, S is equal to square root of epsilon 2 at F is equal to F star on psi 1, psi 2, psi 3, and psi 4, we get following results. And substituting these values in above equation 12, we get equation 13. If the numerator of equation 13 is not equal to 0, this guarantees that the transfer condition hold. Hence, the cofabrication enters into hence the system has enters into cofabrication. Next, fabrication analysis with time delay. Now we consider the system 2 with time delay is sir.
You just stop your presentation and you just go to your equation you have considered and just you explain that equation so that the participant can understand easily.
Oh, okay, sir. From first slide or continue with this slide, sir?
The equation you have considered, Pareto model.
Okay. This is our proposed model. First equation represents the density of prey, represents the density of predator, and the third equation represents the biotic research. This is the integral predation model. Integral predation model means it is a type of prey predator model, and the both prey and predator have another food. Another food, that means biotic resource. This type of model is called integral predation model. Here 1 divided by 1 plus F1B is the fear term. This fear term is reduces the prey, reproduction of prey due to the fear of predator, that is the equation second. Here R1 is the intrinsic growth rate of prey, R2 is the intrinsic growth rate of predator. Here del is the growth rate of W. E1 is the predation time, E2 is the growth rate of predation rate of predator. And N1W, N2W are the carrying capacity of prey and predator respectively. Is it okay?
Okay, come to the conclusion.
Conclusion, okay. This is my conclusion of this paper. In this work, we investigate the delayed integral predation model with received different functional response. Demonstrate the existence of positive equilibrium points, then local stability and the existence of cofabric analysis for non-delayed and delayed model. Finally, the developed theoretical results are numerical simulations. These are my references. Thank you.
So, any questions from the participants? Questions from the participants? Questions from the participants? Then only the session will be an interactive session. Okay. So, if there is no questions, I request Mr. Manikandan to present.
Thank you, sir.
Sure. If you want change, I request T. Devi to present. And you can continue.
Yes, sir. Yes, sir. My slide is visible, sir?
Yes, your slide is visible. You can continue.
Yes, sir. Okay, sir. Good afternoon to all. Let me introduce myself. I am Devi. I am working as assistant professor in mathematics at Builders Engineering College. I am doing my research on soft defects in soft right topological spaces under the guidance of Dr. S. Bharati ma'am. Introduction of this paper. In the year 1999, Mould so introduced the theory of soft sets, and it's useful to solve complicated problems in economics, engineering, environmental science, computer science, and medical science. Abstract of this paper. In this paper, introduced the soft continuous function is soft in soft right topological spaces. Also investigating some new characterization of soft semi-continuous, soft free continuous, soft continuous, and soft beta continuous in soft right topological spaces. Basic definitions of this paper. Soft set, definition of soft set. A pair of set f comma a is called a soft set over x, where f is a mapping given by f from a to f b of x. In other words, a soft set over x is parameterized family of subset of the universe x. For E belong to A, f of E may be considered as a set of soft set f comma a. Next definition of soft topology. Let tau be the collection of soft set over x, then tau is called soft topology.
Excuse me.
Yes, sir.
You just skip the definitions and you go to the main part.
Sir?
Skip the
Okay,
definition
sir. Okay,
and
sir.
you just go to the main part, main theorems and lemmas.
Now, soft B continuous function definition: a soft mapping F from and tritopological spaces if the inverse image of every sigma 1 to 3 open set of Y is a tau of 1 to 3 open set in X. A soft mapping F from tritopological space to X to Y is said to be soft B continuous if the inverse image of every sigma 1 to 3 open set of Y is a 1 to 3 star soft B open set in X. This is the main definition of this paper. Next preposition. Every 1 to 3 star soft continuous function is 1 to 3 star soft B continuous. Next, the theorem, let F from tritopological space X to Y be a soft mapping from a soft tritopological space into a soft tritopological space Y, then the following statements are equal. First one is F is 1 to 3 star soft B continuous. Second one is the inverse image of every sigma 1 to 3 closed set of Y is a 1 to 3 star soft B closed set in X. Definitions of soft semi-continuous. Soft semi-continuous if the inverse image of every sigma 1 to 3 open set of Y is a soft semi-open set in X. Next, soft free continuous. Soft free continuous if the inverse image of every sigma 1 to 3 open set of Y is a soft free open set in X. Next, soft beta continuous. Soft beta continuous if the inverse image of every sigma 1 to 3 open set of Y is a 1 to 3 star soft beta open set in X. And the proposed soft semi-continuous function is soft beta continuous. Next, every soft free continuous function is soft beta. Every soft free continuous function is soft B continuous, but every soft B continuous function is soft beta continuous. But the reverse of this continuous is need not to be true. Conclusion. This paper deals with the properties of 1 to 3 star soft B continuous, soft semi-continuous, soft free continuous, soft continuous, and soft beta continuous in soft right topological space and established the relation between them. Some new characterization of this mapping and investigate prevention properties obtained through this paper. In future, this paper will be basis for further application of soft mapping in soft right topological spaces. Thank you, sir. Sir? Hello, sir?
We are familiar with the topological space, right?
Sir?
In your, we are familiar with topological
Sir,
spaces,
can
right?
yes, sir,
We
yes,
are
sir.
familiar with topological spaces, right? We use tri-topological spaces. We have used tri-topological
Try
spaces. Can you explain
yes, sir, yes, sir.
in by soft tri?
Soft tri-topological spaces satisfying three conditions. Pi and x bar belongs to the set. The union of any number of subsets belong to that set. Intersection of any two subsets also belong to set. These three conditions satisfied. The set is soft topological space, sir. Hello, sir. Hello. Sir.
Can you hear me?
Sir. So no, sir. Tell me, sir. Sir.
Can you hear me?
Ask. Okay, sir. Sir, சொல்லுங்க sir. Yes, sir. Hello. Sir, my voice is audible, sir.
Audible, ma'am. You can proceed. Oh, okay, ma'am.
Okay, sir. Thank you, sir. Thank you, sir.
Mr. Manigandan.
Anna, good afternoon.
Yes, you can continue.
Sir, it is audible. Yes, sir.
Yes, audible. Yes, audible. You can continue, but you should complete within 2 to 3 minutes to explain the equation and your techniques. And finally, you should conclude with the conclusion.
Okay, sir. Good afternoon, sir. My name is M. Manigandan, doing PhD and T. Nandagopal, Assistant Professor, Sri Ramakrishna Mission Vidyalaya, College of Arts and Science. In this abstract, our studies include case of both convex and non-convex mapping based on theorem for multi-value maps. Next one is the introduction, is the basic introductions about the fractional calculus and the fractional differential equation value problem of for fractional differential equation plan to important role in these studies. The equation one is with a condition. Next one is the boundary conditions of equation 2, where zeta denote the capital fractional derivative of order zeta. This is a basic preliminary of first one is Riemann-Leibniz fractional integral of order. Next one is capital derivative of fractional order. Next we move to lemma. Lemma h belongs to C 0,1 of comma r. The integral solution of the linear equation 3 is get the solution of where theta y where rho of equation 4, where we get the equation 5. Proof the general solution of the methods can be written as follow equation 6. Y of 0 equal to 0, y dash of 0 equal to 6. We find b0 and b1, then we get the equation number 7. Condition 8, we get the solution. Substitute the value of b0, b1 and 9 in the 6, yield the solution of 4. This is the complete of the proof. We see the basic definitions of both the inclusions. First definition is the multi-value operator. Second is a subset of L1 of 0,1 is the decomposable if for all u, b belongs to A. And we take some notations for sake of convenience. We say P dash and where theta dash. Equation 10 and 11. Lipschitz case. Assume A1 and A2 we substitute, we prove the condition. Next, we proof to show that the epsilon of f y belongs to q, c of 0, 1, y belongs to c 0, 1. For we get the solution u of n of 13. Thus, v belongs to s f y, and for each 0, 1, we have un of rho gives u rho. Get the equation 14. Hence, there exists of less than or 1. Then there exists v1 of rho belongs to f such that for each rho belongs to 0, 1. Equation h1 of rho is equation 15. By a2 we have hd of f equal to q. So there m belongs to f, rho y bar z bar such that we get the rho belongs to 0, 1. For each rho belongs to 0, 1, let us define h2 of equation 16. Thus f h1 minus h2, we get the equation 17. We substitute our convenient, we get the solution of 18. For consequently, we get h1 minus h2 19. Analogously, interchanging the role of y and y bar, we have obtained the equation 20 since f is a contraction. If following by lemma 2.5, that as a fixed point y.
Come to the conclusion.
Okay. Sir, in this case, we substitute only the two theorems, sir. First one is the Lipschitz case, second one is upper semi-continuous case. In this case, H1 and H2 is defined. H3, H1, H2 and H3 is defined. The solution of finally get the solution of, note that the operator epsilon of f u is q is upper semi-continuous and completely continuous, sir. Two examples. References, sir, using references. Sir, that's all.
So what kind of technique you have used to find the exit?
Sir, Lipschitz case, sir. Yes, sir.
You have used fixed point theorem, right?
Yes, sir. Yes, sir.
What kind of fixed? What kind of fixed point theorem you have used?
Lipschitz case, Larry-Scudder, sir. Scudder's fixed point theorem, sir.
Okay.
Okay, sir.
Any questions from the audience? Any questions from the audience? So if there is no question, I request the next participant R. Sindhu to present her work. R. Sindhu.
Good evening, sir.
Good evening. You can present now.
Good evening, all. I am Sindhu, research scholar in Dr. NGP Arts and Science College. My present the paper is an unsteady MHD viscoelastic fluid past an infinite vertical plate with radiation, chemical reaction, and Soret effect. In this paper, I am presenting the governing equations are solved analytically using regular perturbation technique. The expressions for velocity and temperature, concentrations, fields, or uptime. Introduction, answer of flow. The unsteady flow in which the fluid characteristics, velocity, pressure, or density at a point change with the time. Viscosity is mean that the combination of an elastic and viscous. In radiations is the transfer of thermal energy in the form of electromagnetic wave.
Excuse me. Skip
Example of
the.
light extra.
Excuse me.
Sir?
And you go to your main problem.
Okay, sir. Okay, sir. This is a governing equation. First one is the equations of momentum. Second one is the equation of temperature. Third one is the equation of concentration. This is the initial and boundary conditions. These equations used the boundary conditions solved by these equations. That these equations is a non-linear coupled partial differential equation. So these equations convert to the ODE. Then convert to ODE, this corresponding boundary conditions are involved. The solutions of the problems is this some velocity, temperature, and concentrations. Some conditions are ignored. That is u naught plus epsilon e power nt y1 y plus order of epsilon square. Then temperature t naught y plus epsilon e power nt theta 1 plus order of epsilon square. Then concentration c naught y plus epsilon e power nt c1 y plus order of epsilon square. This is all those ODE equations. The ODE equations, some equate number form functions are involved. Corresponding the epsilon term and constant term separating to the ODE, and corresponding boundary conditions are involved. We get the equations of velocity and temperature and then concentrations. This is a velocity profile for the product number. This product number is increases, the corresponding velocity decreases. It observed that the significations of the velocity is highly near plate, and thereafter it is decreases. And then second figure is a concentrations profile. The concentration profile with the variations in segment number increases, the concentration decreases. And third graph, the temperature profile with variations of radiations are, that is the temperature distribution decreases as radiation parameter or increases. And fourth figure, the temperature profile with the variations in magnetic parameter M, the signification that temperature distribution increases as the magnetic parameter M is increases. Conclude that all these radiations and chemical reactions with Soret effect on unsteady flows, we have to find out the governing equations or regular perturbation technique, and then we have to obtain velocity and temperature and concentration. We have to using Mathematica for find out the velocity profile and concentration profile and temperature profile. This is our the result for graph.
Okay, ma'am. Can you give one example for viscoelastic fluid?
Viscoelastic fluid is honey, ketchup. This combination of viscous and elastic.
The fluid is viscoelastic.
Sir?
Honey is a viscoelastic fluid, huh?
Yes, sir.
Okay, ma'am. Any other question? Any question from participants? Okay, ma'am. Thank you.
Thank you, sir.
There is no question. I request the next candidate, Chandramati, to present her work.
Sir?
Chandramati.
Okay. Good evening. I'm B. Sujata, working as assistant professor in Hindustan College of Engineering and Technology. I'm doing my PhD under the guidance of Dr. N. Chandramati, Government Arts College, Udumalpeta. And my work is on grill nano delta GCAP closed sets in grill nano delta topological spaces. The aim of in this paper, I have introduced a new class of sets, grill nano delta GCAP closed sets, and some of its basic properties are studied. And the concept of grill was introduced by Chowkett. It depends on two operators, pi and psi. Nano topology was introduced by Lillis Divagar, and it depends on the approximations and boundary regions of a subset of an universe with an equivalence relation. Then preliminary is the definition of a grill. In a topological space X, a grill is a non-empty collection of subsets of X and should satisfy the for three conditions. That is, the pi does not belongs to grill. If A belongs to grill and A contained in B contained in X, then B belongs to grill. A comma B is a subset of X, then A union B belongs to grill. That implies that either A belongs to grill or B belongs to grill. If these conditions are satisfied, and it depends on the operator pi and psi, it generates a new topology, that is tau grill, which is finer than the ordinary topology tau. In my definition is I have defined the set on the delta topological spaces, and the operator is pi delta from p of x to p of x to p of x, and this operator together with the grill forms a topology tau delta. Then the nano topology is on the defined on the universal set U with an equivalence relation R. The elements of the U comma R forms an approximation space, and if X is contained in R, then we define the lower approximation denoted by LR of X, and it should satisfy this condition where R is your equivalence relation. Then upper approximation is denoted by UR of X, and using this formula we are calculating the upper approximation value. Then boundary region, which is the difference between the upper approximation and the lower approximation. So with these three conditions, and if it satisfies these 11 propositions, we can form a topology, nano topology tau R of X, which consists of only the 5 elements: U pi, U the universal set, null set, the lower approximation, upper approximation, and the boundary values. Then it forms the nano topological space. So since I am dealing with a delta topological space, I have defined, I have given the condition for closure delta. Then definitions used in this paper is given in this slide. Then my topic is grill nano del GCAP closed sets in grill nano delta topological spaces. The definition is a subset A of a grill nano delta topological space of the nano topology U tau R delta comma delta of X comma grill is called grill nano del GCAP closed set if pi delta of A contained in S whenever A contained in S and S is nano omega open. Then some of the basic conditions. If A and B are a grill nano del GCAP closed sets, then then its union is also a grill nano del GCAP closed set. Then the proof is given, and the intersection is not true. Intersection of two grill nano del GCAP closed set is not a grill nano del GCAP closed set, and it is given in this following example. Then if B is a grill nano del GCAP closed set and B contained in C contained in pi delta of B, then C is also a grill nano del GCAP closed set, and the proof is given here. Then if the grill if in grill nano del GCAP closed set, B is nano delta closed set if and only if it satisfies the condition pi delta of B minus difference B is nano delta closed set. And if B is a nano del GCAP closed set and F is a nano delta closed set, then its union is also a grill nano del GCAP closed set, which is given in the following example. And some of the existing sets, nano topological sets, are compared with my set. That is nano delta closed set, nano regular closed set, nano alpha closed set, grill nano G closed set, or dependent. And the converse is not true. Whereas nano pre-closed set and nano semi-closed set is independent of grill nano del GCAP closed set. And these are some of the references which I have used. Thank you.
So already one candidate have presented the same title, Grill Nano, closed set in Grill Nano, topological space.
Yes, sir.
They are Sujitra.
Yes, sir.
So you are also doing the
The
research
same.
on the same topic.
Same topic.
Right?
Yes, sir.
Can you differentiate the work between these two?
Her set is R omega G set and mine is del G cap closed set, and she has done her research on the topological space. I have taken the delta topological space. That is the difference. She have taken the open sets in the delta. I have taken in the delta open set. That's the difference between our work.
What is the delta topological spaces?
Delta topological, in topology, we are forming the topology, and delta topological space means the closure delta of A must be equal to A. If that collection forms the delta topological space.
Any questions from the audience? From the audience? Questions? The next candidate.
Thank you, sir.
VP. Okay, thank you. I request the next candidate, VP Anandi or G Sandhya to present her work. G Sandhya. You can present now.
Okay, sir. So my screen is audible, visible, sir? Sir?
Yes, ma'am. Yes, ma'am. Visible only.
Good evening to one and all present here. I am Sandhya, doing PhD under the guidance of Dr. P.P. Anandi ma'am, Assistant Professor, Department of Mathematics, Gobiarts and Science College. My topic is image thresholding technique based on a fractional derivative in fuzzy domain. My abstract, fractional calculus on the fuzzy theory or burgeoning field having first application in the fractional derivative are found to detect endlessly. One of the difficulties in using fractional operations is in choosing an appropriate order. Thus, there emerges uncertainty in the deduction fractional edges. To handle this, the fractional edge image is falsified by the falsified edge images. Thresholding or identified for the segmentation. Segmentation outputs of the proposed methods are compared with the latest thresholding techniques by calculating the accuracy and time for the comparison. Results show that the proposed method gives finer output in the lesser time with the compared method. Abstracts. I'm going to main research. These are my preliminaries and basic definitions. Here, the fractional derivatives. There are many different types of derivatives here. Here we using the Groenewald definitions of the fractional derivative of f of t is defined as this, and here I take the the two-dimensional functions for the fractional derivative along with the x and y directions, and these are all my using mask, fuzzy mask. The figure 1 shows the x direction and the figure 2 is direction derivative of the mask. Here I take only two directions and x and y. Here the proposed methodology shows in the figure 3. Here the first image is the original image, then you convert into the, there are two spaces. First phase is taking images into fractional edge image, and the second and then fuzzy set theory image, and then it second phase is resulting the end of the first page, and then the segment image given the thresholding. Then the figure shows that the proposed methodology and then edge reduction, edge of. Then here the 5 step is shows that the edge reduction using the Hessian matrix. The first is taken as the segmentation image, and then using the Hessian matrix for the finding the order, and then I use to find the standard deviation using this equation, and then calculate then eigenvalue matrix to find these equations, and then finally and then fourth step used to these three equations for finding the edges, and then fifth step also used to find the nature direction. Here E is an edge of the given image. Edges in a fuzzy environment. It should be noted that here F is show that the fuzzy membership function. Here E is an edge, and minimum of E is defines an minimum intensity values of the image E, and max of E is defined as maximum image E. Finally, F is an fuzzy membership function. Here mu is equal to 1 minus f of f power 0.2. Here the thresholding value is calculated using these three formulas, and then entropy and median minimum of the membership value, and this parameter this S function is used to find the final segmentation image. And then these are my experiment results. Here there are seven different images based on the different objects, and then use a lot of segmentation method and my proportion methods also. And then these are my results for the other method and my proposed method. Sir? So
You can come to the
okay, sir. In this paper, we have proposed a new technique to segment an image in calculus and the fuzzy set theory. Sure, conclusion then, sir. In this, we have segmenting an image using fractional calculus and fuzzy set theory. Although the proposed technique is found to be an surprise, and the accuracy and the efficiency to the existing multi-level thresholding based on the techniques. A main shortcomings of the method is that in this method, the result of images are found by fixing the number of thresholding as for the future research will be directed towards the automation of the number of thresholding and then fractional orders. These are my reference. Thank you.
participants. There is questions. Is there any question?
Yes, I have a question, sir. Why we need processing in images? Why we need fuzzy into images, huh?
Anita ma'am, your voice is not audible.
Sir, now is it clear?
Yes, ma'am.
Why we need fuzzy into images? I checked in the box.
And the definition.
Sujata ma'am, your question is. Sandhya ma'am, your question is in text message.
Sir, I understand the
Anita
question, sir.
Anita ma'am, yes. Okay ma'am, you can proceed.
Sir, fuzzy set ethical. No, this In the fuzzy set, there are memory function and set is there.
Okay.
Okay, sir.
Madam, shall we? Duraisamy?
Okay, sir. Okay, sir. Okay, sir. Conclude, sir. Okay.
Okay, thank you.
On behalf of the ICGSRC 2021, let us thank our professors Dr. T. Nandagopal and S. Nandakumar for spending their valuable time among their busy schedule. Thank you very much, sir. Dear participants, you can take a break for 5 minutes. Join the validity function after 5 minutes. Feedback link will be shared in the chat box after validatory session. Participants are requested to fill the feedback form without fail for receiving certificates. Thank you.
Thank you so much, sir.
Thank you.
Okay, thank you.
Good evening. Good evening.
Hello.
Sir, good evening, sir.
Good evening. Good evening to all of you.
Good evening, sir.
Good evening. வணக்கம் வணக்கம். நல்லா இருக்கீங்களா?
நல்லா இருக்கேங்க சார்.
Okay, nice meeting you.
Thank you, sir.
This conference.
Good evening to one and all. We welcome Mr. R. Chinnaraju, sir, Assistant Professor, to deliver the welcome address for valediction function. We welcome you, sir.
A pleasant good afternoon to all. I am very much delighted to welcome the President, the Secretary and Correspondent, Principal, Dean of Gobiarts and Science College for their valuable presence. Let me extend a warm welcome to all the eminent personalities and Professor K. Somasundaram, retired professor of Gandhigram Government Institute, for this valedictory session. I am pleased to welcome all the faculty of the Department of Mathematics and also various departments of GASC for being with us today. It's my pleasure to welcome all the participants from various academic institutions who have been with us for a long time for this two-day conference. Once again, I welcome you all. Thank you.
Good evening, Mr. Chinraj.
Good evening to one. I cordially invite Professor Dr. K. Somasun to deliver the valedictory address. Welcome, sir.
Yeah, thank you. Good evening to all of you. My respects to the secretary, president, and my dear friend, principal, Dr. V. Tyagarasu, a long-time friend through the department, as well as personal friend, Dr. Turaisamy, convener of this International Conference on Dynamical Systems and Subcomputing, and Dr. Anandi, delegates, other faculty members of Department of Mathematics in Gobiarts and Science College. And delegates, I'm extremely happy to be with you in this evening on the valedictory session. My appreciation goes to the principal and the conveners, Dr. Anandi and Turaisamy, who are organizing this international conference. It is a credit to the college. I'm also proud that such things are happening in the college where I studied a long time back. Yeah, but if I take the why people organize the conference, and people must know that there are several objectives in organizing a conference like this. Yeah, first of all, the participants are able to share their knowledge, whatever it is. It is maybe a researcher or maybe a good resource person, including me. You know, I also learn from listening to other resource persons. And thereby you are able to connect with people who are working in the real research problems. So this is one of the objective of having or organizing it, and also connecting peers. If you are a research scholar, you will be able to connect to another research scholar or a researcher who is doing in the same field. Number one. Number two, you will be able to know if you are very sensitive and you are very serious in attending the conference. You will be able to listen to researchers from other fields. And if you are listening to resource persons who are giving invited talk, this is very much useful to you, because you will be able to connect mathematics with real life problems. Many cases, I happen to see, because my background is, physics with mathematics and computer science, all these things, I'm able to relate many things and able to see how mathematics works on physics, how mathematics works on real life. So, but those who are really in mathematics, if you're doing a research work in any applied mathematics or soft computing, then the major drawback of all these researchers are they are unable to connect mathematics with real life problems. If you are publishing a paper, the introductory part is the most important one, because that tells what you are going to do, what your new findings are going to do, and where it is being applied. An editor or reviewer who looks into that will be able to identify how good you are in the mathematics and how good you are able to relate your research work to their real life. You may do very good research unless you are able to relate that result to your real life. The chances of getting rejected or accepted is very less. If you show that your results are directly hitting real life problems and matching and trying to solve problems, then it is highly likely that it will be accepted. Because when I review a paper, I look at that also. Though it is from different point of view, but I will assess an author and a researcher how good they are in this research by reading the introductory part alone. Because therefore, By attending this kind of conference, the researchers are able to learn where mathematics works really. So therefore, the conference gives a very good opportunity for the participants to learn more, because there is a saying in Tamil, Kattalil Ketralin Nandru, because what you need to spend 6 months, even 1 year to learn something, you will get the same knowledge by attending a couple of innovative lectures. Such is the importance of attending a conference like this. and then when I come back to the mathematics itself, because you all know that I used to tell stories. No, I did my research in Department of Applied Mathematics, but I really come from physics. And therefore, whenever I sit in my research room, there used to be a debate. There is one professor who is retired now from IIT Madras, is called as Dr. C. Pandurang, and he usually comes and tells, okay, so guys, those who are studying mathematics, who studied mathematics, are all having extra gene. Others don't have such thing. So I really appreciate those who studied mathematics or having really an extra gene, so to say. They have extra knowledge. But day by day, what happens is that people are, deviating from pure mathematics or even applied mathematics to other kind of thing, like moving towards soft computing, because that is very easy to publish a paper, but don't come that too far away from your mathematics. A country relies on the how the knowledgeable people are in that country. Mathematics is one such subject which generates a very huge knowledge, new knowledge in a research sphere. So those who are having a good knowledge in mathematics, even if it is not applicable to a real life problem, but do concentrate, because one day, maybe after some time, say for example, if you take several applications which are all being used in computer science or not being considered over centuries. For example, there is a wavelet theory by Mallet. So in 1980s, this guy, Mallet, what he did was he just took that wavelet packets, and he is able to show that it can be implemented in electronic circuits. So, but for his invention or rekindling of these wavelets, the cell phones now, which make use of compressing the sound signals, is not possible. Why? Because he is able to relate the electrical engineering to the mathematics, to how you can convert the mathematical theory into an electronic circuits. So that's why I said, generating a knowledge and having a mathematical knowledge is always helpful and always leads any kind of theoretical work. Without mathematics, you cannot progress in theoretical work and generating new knowledge in that area. So therefore, Indian government used to have some kind of incentive by giving scholarships to mathematical students. I'm not sure whether still that is being pursued for higher studies in mathematics. For example, even in Gandhigram Institute, the Department of Atomic Energy used to give supporting mathematics by giving a grant of something like 3 to 4 lakhs of grant for buying books alone. So we must also groom, as mathematics teachers who are all here, should groom students and researchers who are doing good mathematics. And thereby, not only you are grooming the students, but we are also grooming youngsters for the future of India as such, because knowledge is a power which we used to tell. Mathematics gives such a knowledge to the country. And finally, before we move close up, I just say a few things. I don't know how the other people relate mathematics to real life problems. All of you know that the simple harmonic motion, free simple harmonic motion, d square y by dt2 plus minus omega square y equal to 0 is a free oscillation wherein it's an ideal condition. So I'm just telling how you relate but that is not a realistic situation. Suppose if air is present, it prevents the motion of the oscillations, thereby we call it as a damping. Suppose if something is oscillating inside a mud, inside a fluid, then the free vibrations are being damped by this fluid, therefore we call it as a damped oscillations. For that, what we do is, it is proportional to the velocity of the velocity or the rate of change of displacement. Therefore, we put an extra term for the velocity by adding, say, omega, say gamma. Gamma is a damping factor multiplied by the dy by dt or the velocity factor. So it becomes d square y by dt 2 plus gamma into dy by dt minus omega square equal to 0. Suppose if you take a speaker that you have in your earphone or in your radio or your cell phone, the speaker is having an forced oscillations. So in addition to this, you are forcing a system to oscillate. Therefore, this equation, second order differential equation, d square y by dt 2 plus gamma into dy by dt minus omega square y is not equal to 0, but rather a function, a sine function, so that it forces the speaker to vibrate. So it's a forced oscillation. So that's how the mathematics is able to apply to real life situations. So my request to all the participants is, when you do a research is good, that is a pure research, but don't go with that. But please see where your results are applicable. And do not jump to ad hoc mathematics. So what is an ad hoc mathematics? Ad hoc mathematics is one which you will use or derive empirically, and that is applicable only for such situations. When you want to extend to other, beyond that, they use such ad hoc mathematics like algorithm develop will not work. But if you develop an algorithm purely based on mathematics, it can be extended, scalable. Therefore, you go for it. And find application, read more of the practical applications where mathematics works. Well, such things will help you in the long run to publish good papers, in the long run to learn by yourself how the mathematics works. Because many times I asked, in lectures, how you relate the dy by dx, the slope in real lives. Because in image processing we use how to find the edge of an image, but many times people are unable to give a simple answer for that. Therefore, don't go with that. Every mathematics, simple mathematics, has a real life application. Learn mathematics with meaning of it. That will give you a very high understanding of mathematics. I wish the participants to go with, I think they should have learned quite a lot of topics, should have interacted with other groups. If not interacted, at least we have addresses of those participants who took part in this online conference. Have them, contact them, interact with them. If you have got contact with your research persons, please do. It is a chance for you to interact with them, so that what you need to spend months together, you can learn and get clarified within a couple of hours. I wish you all good luck for participating in this international conference. I thank the management of Gobiarts and Science College, the president, the secretary, in particular to the principal, Professor Tyagarasu, and the organizers, the two organizers, Turesami and Anandi, who invited me for this lecture, and all other faculty members and delegates for giving this opportunity to talk to you. Thank you all.
Thank you, sir. This is a more valuable and it is very effective for us. Next, I privilege to welcome our honorable principal of our college, Professor Dr. V. Tyagaraja, sir, to felicitate the valedictory function. We welcome you, sir.
Respected and revered President, Secretary of Gobiarts and Science College, today's chief guest of the valedictory function of International Conference on Dynamic Systems and Soft Computing, Professor Dr. K. Somasundaram, former professor, Department of Computer Applications, the Gandhigram Rural Institute, Dindigul, Mr. R. Chinnarasu, Assistant Professor of Mathematics, who proposed welcome address, Mrs. Ageshwari, HOD of Mathematics, Dr. P. Duresamy, convener of the International Conference, and Dr. V.P. Anandi, who is going to propose vote of thanks, and convener of the conference, delegates, faculty members of the Department of Mathematics, and all the participants all over the world. I am happy that more than 72 researchers in all over the world, they participated in the international conference organized by the Department of Mathematics. I hope you all received a number of information in the sessions for the past 2 days. I'm happy that Professor Dr. K. Somasundaram, the legend of computer science and mathematics, who proposed a valedictory address with a number of information to the researchers. I hope the information given by our valedictory address chief guest, Professor Dr. K. Somasundaram, will reach all the researchers to go further. I'm happy that the department organized a conference even during this pandemic situation over online. I sincerely congratulate convener and the faculty members of all the departments for organizing events. I think this conference will be useful to all the researchers. I hope everyone enjoyed the sessions. This note, I conclude. Thank you.
Thank you, sir. Now it is time to invite Dr. P. Duresamy, sir, convener of ICDSSC 2021, to deliver the report of the conference. Welcome you, sir.
Good evening to one and all present here. International Virtual Conference on Dynamic Systems and Soft Computing 2021, a two-day event, took place on 5th and 6th March 2021, organized by PG and Research Department of Mathematics, Gobiarts and Science College, Kobichetipalayam. The conference was multidisciplinary in nature, incorporating dynamic systems and soft computing in all engineering and scientific disciplines. The conference was formally inaugurated by praying the Almighty. The mechanics of the conference was elaborated by Dr. V.P. Anandi, convener, ICDSC 2021. The welcome address was given by Mrs. P. Uma Maheshwari, Associate Professor and Head of Mathematics, GSC. In her address, she emphasized the importance of conduct of the conference and also requested the participants to make use of this opportunity effectively. Professor Dr. V. Tyagarasu, Principal GSC, delivered the presidential address. He remarked the achievements made by GSC in his speech. Prem Dharnidharan, Secretary and Correspondent, and Dr. R. Chellapan, Dean, GSC, considered the gathering. Head of the Department of Mathematics introduced the chief guest, Patnaikar Awardee, Professor Dr. M. Lakshmanan Sir, Professor of Eminence and DST Sir, Distinguished Fellow, Bharadasan University, Tiruchirappalli, to the delegates. The chief guest shared his experience and he pointed out the real learning is only by stimulating, cultivating, and applying knowledge from industries. Vote of thanks was given by one of the conveners, myself. The conference has served as a platform for the mathematicians, engineers, and scientists to present their findings and to exchange their knowledge with scientists from among 117 participants. 42 had presented their research findings. On the first day of the conference, we had 5 invited talk sessions. The first invited speaker, Professor of Eminence and DST Serve, Distinguished Fellow, Bharadasan University, Tiruchirappalli, who spoke on nonlinear dynamics and evolving science. Started with Lie symmetry analysis of fractional differential equations by Dr. T. Bhagiraj, Indian Institute of Information Technology, Kerala. After a break, third session was handed over to an international speaker, Dr. T. Chatiraj, Gosu University, China. He emphasized the ideas on qualitative behaviors of delayed differential equations with perturbation of matrices. Fourth invited talk was delivered by Dr. P. Muthukumar, the Gandhigram Rural Institute, Dindigul, on the emerging trends in the field of dynamical analysis of predator-prey models. The last invited talk of the first day ends with an international speaker, Dr. Demi Nagel Bosco, Universidad Hostel, Rosario, Argentina, on fractional calculus, scope, futures, and interpretations. The second day started with an active and energetic young researcher, Dr. P. Prakash, Amrita Visva Vidyabhadam University, Coimbatore. He explained invariant subspaces and exact solutions of nonlinear fractional partial differential equations. The next session began immediately with Professor Dr. P. Palasubramaniam, Director, International Program and former Registrar, the Gandhigram Rural Institute, Dindigul, who is the recipient of Tamil Nadu Scientist Award and Tamil Nadu Senior Scientist Award. He explained role of fractional calculus in neural network and image processing. The final invited talk ends with kind-hearted Professor Dr. K. Somasundaram, the Gandhigram Rural Institute, Dindigul, on image compression. After the talk, the parallel paper presentation sessions were started with 42 participants from various institutes. The session 1 had been observed by Dr. T. Nandagopal and Dr. S. Muthukumar from Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. The another parallel session had been chaired by Dr. S. Iswaramurthy, Dr. NGP Arts and Science College, Coimbatore, and Dr. M. Sivabalan, Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. The valedictory function began with the welcome address by Mr. R. Chinraj sir, Assistant Professor of Mathematics, GSC, and he introduced the chief guest, Professor Dr. K. Somasundaram, the Gandhigram Rural Institute, Dindigul. After the valedictory note given by the professor, the valediction of ICDSE 2021 was felicitated by our esteemed principal, Professor Dr. V. Tyagaraja sir. Finally, feedback was given by the participants. It was a moral boost to the organizing committee.
Thank you, sir.
Thank you, sir. It is time for feedback session. Participants, please give the feedback for this international conference.
Good evening to one and all. I am Dr. M. Sobolan, Assistant Professor of Mathematics, Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. First of all, I thank and congratulate the organizer for conducting wonderful the international conferences. It is very useful for the young researchers to the research in the fields of nonlinear dynamics, analysis of fractional differential equations, dynamical analysis of prey-predator models, roles of fractional calculus in neural network and image processing and image compressions. Nowadays, students are interested to take the researchers in these kinds of fast growing areas. So this conference to give a platform to the young budding researchers in the fields of mathematics. These 2 days, all the eminent scientists are wonderfully shared their knowledge and experience with us. I thank all the speakers and organizers of mathematics departments of Gobiarts and Science College, Kobe Settipalayam, for giving this wonderful opportunity, and thank you once again.
Thank you, sir. Please, any feedback from delegates?
Good evening, sir.
Good evening, ma'am.
It's a golden opportunity for participating in the International Virtual Conference. The seminar are informative. The topic given gives ideas for our higher studies. Thank you so much, sir.
Thank you for your valuable feedback. Delegates, any other feedback?
Good evening to all. I'm
Good
Sandhya.
evening, ma'am.
This is my conference in GAC. I feel this conference is very useful for me because the title and speakers are very useful to give the such an information. And I convey the gratitude to the organization for the giving an opportunity. And thank you all.
Thank you, ma'am. Thank you. Any other feedback?
I'm Brindashri. I have presented a paper here, and all the invited talks are very useful and very informative, and it will be very helpful for my higher projects. And thank you so much, sir, for conducting this conference in this college. Thank you, sir.
Thank you for your feedback. Please, any other feedback?
Good evening, sir.
Good evening.
I'm Dharani. Both first and second day conference session is worthable and we gain a good knowledge over it. Thank you for organizer who conducting the international virtual conference beside this pandemic situation. Thank you all.
Thank you for your valuable feedback. Delegates, please, any other feedback? Thank you so much for your feedback.
Last but not least, now it is time to express our gratitude. I welcome Dr. VP Anita Ma'am, convener of ICD SSC 2021, to deliver the vote of thanks.
Good evening, everyone. I take immense pleasure in proposing vote of thanks on this eve of valediction. The virtual international conference paved the way to discuss the priority issues involved in the study of dynamical systems and soft computing. I would like to take this wonderful opportunity to express my sincere thanks to Professor Somasundaram sir, who have rendered valuable suggestions and illuminated the minds of young researchers in this valediction. Thank you so much, sir. I thank our beloved principal for honoring us with this, with taking his busy schedule to felicitate the validity function on this conference. I deemed it a great privilege to thank our management and dean for their moral support. I thank the members of the advisory committee for their suggestions. I represent a heartfelt thank to our head of the department for her continuous support. I am thankful to the steering committee members of ICDSSC 2021 for their tireless support till the end of this conference. I place on record our deep, sincere gratitude towards the keynote speakers and session chairs whose effort paved a way for the enlightenment of our mathematical community. I thank our IQAC coordinator for his relentless support. I thank the software developer and non-teaching staff members who have worked hard to ensure the technical quality in all the sessions of this two-day international conference without discontinuity with live streaming. I also thank our students and research scholars for their help for organizing this conference. Last but not least, I thank all the delegates who has acted as a pillar of this conference. Without your support, we cannot make this conference a great success. Thank you all. Thank you once again.
Thank you, ma'am.
Okay, thank you. The feedback for the overall feedback link has been posted in the chat box. Delegates, you can fill it without any mistake, because that through that link only we can give certificates. So if there is any mistake, so we cannot able to do anything. So fill the form very carefully without any errors. Okay, thank you. We thank all the delegates for your patient listening till this today. So thank you all once again. If you have any queries, you can ask about certificates or anything, or presentation or publication now.
Thank you so much, sir, Dr. Nandagopal sir and Dr. Muthukumar sir, Dr. Shivabalan sir, attending this valedictory function, and also thanks to all the participants. Thank you so much.
I think no delegates have difficulty, I think, in filling the feedback form. So I think we can wind up the session. After reviewing all the papers, then we can again mail you about the publication and acceptance of the paper through email. Yeah, we will post it again, sir.
Ma'am. Ma'am.
Delegates, you can leave the meeting.
Ma'am, are you hear me?